Okay. Michael and Samantha, if you don't mind, I just wanted to introduce you to our group as we're coming back from lunch. So everyone, I have the pleasure of introducing Michael Wong and Samantha Menard from EQ Building Performance. This is a consulting firm that does a lot of work helping buildings achieve some really fantastic energy results in the built environment. Both Michael and Samantha are involved with their energy team. And I've seen this or a similar slide deck in previous weeks at BBBC. So I'm thrilled you're all going to get the opportunity to review this information. It will be extremely valuable as you all go towards developing your building proposals. So, Michael, Samantha, take it away.
Hi, everybody. I don't know what time you guys started at, if you guys just had lunch, but I hope you're all having a great day so far. So yeah, Michael and I are going to be doing this great presentation on energy modeling and kind of what it is and what you can use it for, its strengths and its weaknesses. I'm going to do a bit of an introduction and then I'll pass it off to Michael. I don't know who was on in the last like 10 minutes, but if you have any questions, please put them in the chat and Michael or I will try to answer them as the presentation is going on. Or if it's a bigger question, we might save it to the end and address it there. But yeah, let's dive into things. So just a little bit of background on who we are. So my colleague Michael Wong is an energy specialist on our team, and he has a background in environmental engineering from Waterloo and a master's of applied science in building science from TMU. I am the project director of energy and carbon at EQ, and my background was originally in architecture at TMU back in the day, but I've been in the energy modeling industry for more than 10 years, and we both work at EQ, one of the largest multidisciplinary engineering firms in the GTA. And we specialize in energy consulting, sustainability, commissioning, specifically in the high-rise residential realm. We do dabble a bit in other things like commercial and industrial, but that's our main bread and butter. And we have about a team of 25 people with a variety of different backgrounds. So our learning objectives today is to understand what energy modeling is and its purpose in design, explore the energy modeling process and its role in decision making, compare and understand the different targets. I have in here like the relative versus performance. You might not know what that means yet, but you will by the end of this presentation. And then identify some key codes and standards that you might interact with if you're doing energy modeling. So what is energy modeling exactly? I'm sure some of you may have heard about it. Some of you might have experience with it. Some of you might not even know what it is at all. But we'll dive into it. So what it is basically a tool. How you use it is kind of up to you. It takes inputs from a variety of different things, like what your building looks like, what the weather conditions are for where you are, what mechanical systems you have, internal loads like lighting, equipment, what people are there, how often they're using hot water fixtures, if there's, if it's like a lab, what equipment's in there, all of those things, and simulates what that would look like. We add operating schedules for like how often people are there and how many people are there. Different simulation things have different inputs as well. Like you can have like shading and a lot of other things, and it basically puts it all together, spits out a lot of different results. Those different results can vary. You'll always get your energy use, but you could see load profiles for when the building is peaking. You can look at, then calculate your carbon usage. You can help see sizing for equipment. There's a lot of different things that come out of it. The main energy modeling systems that are used are Energy Plus, eQuest, and IESVE. Open Studio is a tool that can be used with Energy Plus. The most common right now are Energy Plus and IESVE. IESVE is a proprietary software, while Energy Plus and eQuest are both open source, so they're free to use. They're developed by the Department of Energy in the US. We use Energy Plus more at EQ and like it a little bit better than some of the other ones, just because you can write some of your own scripts and do a little bit more back-ended stuff to customize it. But for whatever you want to do, there is a tool that can help you do that. But why would we do energy modeling. So there's kind of three main categories as to why you might do modeling. The first would be to demonstrate minimum compliance with something. So the Ontario Building Code, a lot of other jurisdictions in Canada have building codes as well, mandate a specific energy use. There is like a prescriptive path where if you just check all the boxes, you're good, but it's extremely strict and has no leniency at all. So what you can do is say, hey, my building's using this much energy. If I had built it prescriptively to what this checkbox says, it's using more energy. So because I'm less than that, I'm okay. You kind of trade off your performance via an energy model. Same with Toronto Green Standards or other municipal green standards. Similarly, like they'll say, hey, you have to beat this minimum performance. You perform a model to say, hey, I'm using less energy than you told me I'm allowed to. So I'm all good. That's kind of the thing that most projects, if we're getting on board, because it's required. The next reason why you might want to do energy modeling is if you want to do a little bit more than what's minimum. So next slide, Michael. That would be pursuing a high performance certification. So if you're familiar with the Toronto Green Standard or some other municipal green standards, usually there's a minimum performance and then they have an incentive to do a higher performance one. In Toronto, that's called tier 2. And developers can get some money back by doing this higher performance tier. The Savings by Design program, which you'll all be at a charrette on Thursday. We will be there as well. LEED certification, the Zero Carbon Building Standard, or other incentives as well. Like the Canadian Mortgage and Housing Corporation has quite a few for rental projects where they can get really great financing and affordability on affordability, energy, and accessibility if they can meet those targets. The kind of third category, which overlaps with the others, is to explore the building performance itself. So sometimes you just want to make a better building or you want to optimize, like, hey, we're trying to figure out which design works better for us. Should we go with this mechanical system or this one? What are the operating costs for that? What kind of equipment would I need? So for that, we kind of look at parametric modeling, existing building, calibrated modeling, and energy audits. So that maybe you already have a building that exists and you want to reduce your energy and you want to kind of see what impact some stuff might have. That can help with that. And then predictive energy modeling. So seeing like, okay, how much would I be using for that? And I saw in the chat, Bettina was saying parametric modeling is so cool, and I totally agree, which is why we've got our next slide on it. So this probably looks crazy to a lot of you. If you look at there's kind of like where the inputs and outputs are. The inputs are all of the different things you might want to look at in a model. So, we've got this first column, we've got 3 different mechanical systems. We've got window to wall ratios, different wall performances, infiltration savings, different heat recovery options, some lighting and domestic hot water things. And, you could model some packages of that, but that could be very time consuming to put all of that together. So what parametric modeling does is model every single iteration of all of those things together and then give you the results, these outputs. So this is your energy, thermal demand, carbon, what TGS tier you're hitting, and what your energy costs are. So this here is 350,000 different energy models all put together. So you can really like optimize the design as much as you want. It's a really great tool. It takes a little more time to do, but it can be really life-changing on a project. But now I'm going to pass it over to Michael to talk about how we actually measure that performance.
Okay, awesome. Thank you so much. Yes, so we spoke a lot about some of the differences of like the types of models, and Sam already alluded to like some of the outputs that we can get. So specifically when we're modeling and we're talking about building performance, what do we really want to know? What are we trying to measure? And here's just 4 common metrics. Obviously, there's a lot more that people look at, but these are probably the most common that you'll hear in industry. I think the first is pretty obvious. It's just your building energy. So it'd be your total building on-site energy, and this accounts for all of your fuels. Most commonly, that's really just electricity and natural gas. Sometimes it might include propane or something if you might be in a remote location. And this would account also for your renewables. So anything you generate on site would be subtracted from that value. Next, we have your GHG or your carbon emissions. So I'm not sure how specific and technical some folks are, but there's mainly two types that we typically consider, which would be your scope 1 emissions, which is all of your emissions generated on site from natural gas combustion, like from boilers or furnaces. And then there would be scope 2 emissions. So how much emissions did you contribute to via how much electricity you pulled from the grid? So in Ontario, our grid is mostly made up of hydro and nuclear, which is so much so why people call electricity hydro here. And those are both fairly clean in terms of carbon emissions. However, if we took the same building connected to the grid in Alberta, its emissions would be much higher because their grid emissions are still mostly natural gas, and I think some coal too. So your location really matters when people start to talk about things like electrification. And speaking about electrification, something to always keep in mind is your building peak demand. So what is the peak electrical demand of your building, which does get challenged more and more as buildings are starting to look into electrification, which can really increase that peak demand, as well as may put strains on the provincial electrical grid, which could potentially impact future utility pricing, and then maybe how much future generation the province may want to include. And then the last would be your utility costs. Pretty straightforward. It's just the total cost of purchasing your utilities. But one thing to note is that electricity currently is about 5 times more expensive than natural gas in Ontario. And the carbon tax initially was intended to help reduce this cost gap between gas-based systems and electric-based systems, to essentially encourage people to look more at electrical systems once the costs were more comparable and once they were more similar. But without that, it could become a little bit more challenging to kind of make the business case for electrification, although it is definitely still there. And that's partially our job to help demonstrate the benefits of that. So with those metrics, Samantha was talking about the building code earlier as one of the minimum standards that we use for determining compliance and to help ensure that we have minimum energy efficiency targets. And so older modeling codes and standards like the building code require us to evaluate our performance against some reference energy code to determine some percentage better than savings. So what this means is we're required to look at some energy codes like the NECB, National Energy Code of Canada for Buildings, or ASHRAE 90.1, which is just the section of ASHRAE dictating energy efficiency. And this will require us to build a code equivalent reference model that we can compare our actual design against to evaluate this our performance against the code reference to determine some minimum percentage of savings. And this is what a lot of older codes use, but we're seeing a bit of a shift in the industry towards what are called absolute performance metrics. So I'm not sure if some of these may seem familiar to some people, but I'll still talk about them briefly anyway. Your EUI, energy use intensity, sometimes also called TEUI or TUI, just for total energy use intensity. It's the same thing as your energy, except now we're taking that total energy and dividing it by your total per unit modeled floor area. And so the advantage of absolute targets are because they just take your total building consumption and distribute it across your total modeled floor area. It becomes a lot easier to compare between different buildings. So for instance, if I had a project that said it had 20% savings and a project that had 15% savings, the project that actually has 15% savings could potentially consume much less energy than the one that even had higher savings. So absolute targets kind of helps let us compare that a little bit better, especially compare different building sizes. There's a lot of great advantages to absolute performance that I'll get into, but I'll just keep running through these a little bit. GHGI is just your total emissions now per unit model floor area. The TEDI is your thermal energy demand intensity. This is a slightly different metric and a little bit newer too in industry, so I'll talk about this on the next slide. But it basically takes your total building heating demand per unit model floor area as well. And then the last is just your energy cost intensity, so your total utility cost divided by your floor area. So what is TEDI and what is thermal demand? So let's look at this example of a house where we have about 10,000 kilowatt hours of heat loss. And this will be heat loss through your building enclosure, so through your windows, through your roof, through your walls, through the floor slab, as well as any ventilation or infiltration-based losses. So ventilation through any like mechanical systems, or maybe just through cracks or infiltration or exfiltration. And to satisfy this 10,000 kilowatt hours of heat loss, let's say the owners of this house used an 80% efficient gas furnace. So this would result in about 12,500 kilowatt hours of heating energy, all of which would be natural gas. But if the exact same house with the exact same amount of heat loss wanted to install a, let's say, 200% efficient air source heat pump instead, this would be about 5,000 kilowatt hours of heating energy, all of which, or maybe most of which, would be electricity. And so between these two systems, there's about, the heat pump obviously is much more efficient. It's about 60% more efficient, and probably has over 90% carbon savings, potentially, depending on where you are in the country. So very different energy profiles, but this amount of heat loss was static. This did not change. And this is your thermal demand. So your thermal demand does not actually consider the downstream mechanical equipment efficiency. It really just kind of looks at where the original sources of heat loss were occurring within your building. So simply put, the thermal demand is the amount of heating your building requires from your mechanical equipment without considering equipment efficiency. And the TEDI is just your thermal demand per unit floor area. So with these, all these absolute targets, or sorry, with these absolute metrics, we need to develop absolute targets, which are pre-developed intensity-based targets for specific archetypes in a certain geographic region. And so, oh, I see Bettina just posted as an example some of the different targets that the Durham region uses in the chat, which is great. And so when I talk about specific archetypes, what that basically means is a very common building type that we see gets repeated and has very similar characteristics, very similar and repeatable characteristics. So some of the most common types would be, you know, something that we see very often. So like a low-rise residential building, a high-rise residential, commercial office, commercial retail, and typically speaking, K through 12 schools. These typically have a lot of the same kind of composition and massing enough that we can develop archetypes that are easy to compare to targets, because all the buildings are, relatively speaking, so similar to each other. We'd spoken briefly about the Toronto Green Standard, which I think you'll hear more about also. But just as a little bit of a sneak peek, here's some of the, I'll be referencing it a lot, specifically as a bit of a case study / example, because we're very familiar with it. It's one of the dictating green development standards in the region, and it was also very influential in encouraging other municipalities in the region to develop their own green development standards. So on the left-hand side are some of the building characteristics that the team used to figure out what they want their targets to be, based on kind of varying different levels of performance from the envelope, mechanical systems, like Samantha was saying, all these other various different inputs that help define the model. And then with that, they determined different energy, EUI, TEDI, and GHGI targets across different versions and tiers, which will help create their path towards net zero buildings within the city of Toronto. So just a bit of an overview between relative and absolute targets. Relative targets are applicable to pretty much all building types, anything that you can read and reference within the energy code. But absolute targets require archetypal building types so that you can generate those specific targets for each building type. Relative targets are applicable to all climates generally, versus absolute targets do need to be generated to be climate specific. So if we wanted the same building might comply with the targets here in Toronto, but then if we wanted to use the same general level of performance, the targets would look quite different in, say, Alberta or Ottawa, where the climate is much colder. Relative targets are based on energy codes like NECB and ASHRAE, but absolute targets, like we've said, were based on predetermined archetypes that will need to be developed specifically for each archetype for each climate region. And something that I didn't touch on yet, but I think will be interesting to note for now and as well as for later, is that when we're using relative targets, a lot of the times these codes were written as pass-fail systems. And in many cases, they actually penalize heat pump technology. So as we're actually actively trying to electrify and decarbonize and improve building performance, sometimes your percent savings can actually go down instead of up, just because of the way the code is written. It doesn't necessarily want to let people, for instance, use a very poor performing envelope, but then a very high performance mechanical system, and then instantly pass and achieve building code. Versus absolute targets, they typically reflect the building design well, so it doesn't really matter where the trade-offs are occurring. It should be relatively reflected within your different energy metrics. And I was saying earlier also, relative targets sometimes have inconsistent savings, both in the sense that you might look at two models with percent savings and think that just because one is higher than the other, that it's better energy performing, but that's not always true. But then always within that, it can get really complicated sometimes to navigate different codes. So 30% better for ASHRAE is not necessarily 30% better for NECB, as well as within that, there's different versions of NECB, different versions of ASHRAE. Some regions and municipalities have different addendums that stack onto that as well. So that can be very confusing, but absolute targets are typically a lot easier to compare as long as they follow the same core modeling principles. And last, I want to talk also about that because relative targets have a proposed design that we compare against a code equivalent reference. If we want our percent savings to increase, we could do that by either improving the design, or sometimes if we want to gamify things, and I'm not saying we do this necessarily, but this definitely does happen in industry. A lot of people may just sometimes make the reference as poor performing as possible to increase your percent savings. And then with absolute targets, that's not really an option because we are only considering the designed building performance against its floor area. So that really requires us to focus and hone in on just improving the building design as much as possible. So gonna pivot and talk about some different codes and standards, as well as some of the factors and differences between them. So looking at thermal bridging, different codes require different levels of thermal bridging accounting. And for anyone who may not know, a thermal bridge, very simple definition. Someone else can potentially come and disagree with me later about this, but I like to just kind of simplify it and say a thermal bridge is essentially any interruption in the insulation that acts as a bridge for heat transfer. And so the level of thermal bridging that we account for in the building code is quite minimal. But a lot of the newer standards, such as Toronto Green Standard, Zero Carbon Building, and Passive House, require really extensive thermal bridging accounting for all types of different building details across the enclosure. And so just for context, to highlight some of the differences, depending on how much accounting for thermal bridging you include in your modeling, you may only actually be estimating about 50% of the building heat loss through your enclosure. So depending on kind of like the scope and the rigor of which modeling standard you're referencing, you may only be accounting for just a fraction of how much heat loss is occurring in your enclosure. Somewhat similarly, when we're talking about outer air ventilation rates, building code, just again as an example, requires models to account for minimum ventilation rates. But in reality, most buildings are actually overventilated, especially in tall residential buildings where they used highly overpressurized central corridors to combat stack effect and odor transfer. So depending on which modeling code or standard you may be referencing, the difference between minimum ventilation rates and design ventilation rates can sometimes be, on the low end, maybe 4 times as much ventilation, but on the high end, we've definitely seen somewhere between like 10 or 12 times as much ventilation from the design compared to minimum code ventilation rates. Looking at flow fixtures, different standards have different methods for accounting for flow fixture estimates, but the building code specifically does not even allow you to take credit for low plumbing fixtures at all, even though there are different studies that have shown that it can actually have a very material impact on your, how much water you consume, which is great, but also that would minimize your amount of domestic heating energy as well. And then when considering infiltration, it really drastically differs between the design and the final constructed product, just because there are a lot of different ways to improve building infiltration, such as with the use of prefabricated construction practices. There's also some great technologies out there that improve building infiltration, but a lot of it really just comes down to your construction quality. And different standards assume different baseline infiltration rates, but these don't necessarily line up with the final constructed product either. And what's really challenging also is that kind of specifically within the space of like, tall and large buildings, there's very limited information about tested tall buildings within the GTHA. So we're still relying a lot on just kind of like baseline default assumptions for that. And then last, looking at occupancy schedules, occupancy and tenant behavior is pretty much impossible to predict. Mostly our models rely on predetermined averaged schedules of anticipated occupancy and behavioral usage. They're generally correct on average, but they don't always capture extreme cases and sometimes new behavior. So for instance, yeah, there's my laser pointer. When we're looking at the occupancy trend here, which is the blue line, I would kind of intuit that this is maybe a residential schedule where people are pretty much here all hours of the morning and the night, maybe as they're sleeping or waking up, getting ready for the day, but mostly gone in the middle of the day, as people would have gone to work traditionally. But how have these residential schedules shifted, for instance, let's say, to account for increased work from home patterns over the last couple of years? So some of these schedules may be out of date, but potentially a great research project for somebody to really look into. But it's still a lot of the industry relying on these pre-established averages. And just as a fairly quick comparison between just 3 specific codes, as an example, I looked at the Ontario Building Code, LEED v5, and Toronto Green Standard version 4 tier 1, which is the current minimum requirement within the city of Toronto. I want to look at all 3 kind of as a bit of a spread of what we're seeing in industry and how these 3 different codes and standards all kind of relate and stack up against each other. So OBC and LEED v5 both are relative targets. They both reference a different version of ASHRAE. LEED v5 references 2019, but the Ontario Building Code actually references ASHRAE 2013, which I do want to note is not only a 12-year-old standard at this point, but the Energy Code actually hasn't been updated since 2017. So it's a little bit out of date, which I think you'll be seeing as we discuss some of these different targets. So from an energy perspective, the Ontario Building Code actually only requires you to just be equal to or better than the code equivalent. LEED v5 kind of has a bit of a sliding scale because they award different points based on how well you perform. And TGS has its own specific absolute targets. The targets I used here were for the high-rise residential archetype. So your carbon or greenhouse gas emissions, similarly, just equal to or better than code. LEED v5 doesn't have a specific target, but it does have a separate credit that encourages electrification. And Ontario Building Code also, once again, just another 0. You only have to be equal to or better than the code to achieve building code compliance. LEED v5 has a separate credit for peak reduction measures. And interestingly, Toronto Green Standard doesn't have any considerations for peak electricity. And this is actually fairly common for absolute targets. I believe it's because the committee that put together these absolute targets kind of found that it was really challenging to characterize peak electricity per unit floor area. And it really drastically differed between different archetypes. So I think they didn't, I think it was too complicated. So they kind of didn't include it as a direct consideration. And then when we're talking about thermal bridging, yeah, the Ontario Building Code, or thermal demand, I'm sorry. The Ontario Building Code does not have any considerations at all for this. This is somewhat of a newer consideration. LEED v5, once again, has another credit. LEED is a credit-based system, and this credit awards points for improved ventilation, airtightness, and reduced thermal bridging. And here are the 3 key energy targets for Toronto Green Standard. So already, I think we can see that not only the Ontario Building Code references a much older version of the energy codes, 2013 versus 2019, and TGS was the first version of these absolute targets were developed in 2018. But in addition to that, these targets are quite lax. They're really only asking just for minimum compliance. And I'm not sure if this has already been said, but someone said this and I really like it, is that the Ontario Building Code dictates minimum performance, which means when something is built to code, another way to say that, maybe pessimistically, but I like it, is that a code compliant building is legally the worst possible building that you can build. And I think that's kind of demonstrated here with all of these zeros as well. They're not actually asking for exceptional performance by any means. And then considering some of the other different factors that I had discussed. So when we're looking at full thermal bridging, Ontario Building Code does not account for that. They ask for minimal. Ventilation rates, they just want you to consider the minimum ventilation rates instead of making engineering estimates about the approximate design ventilation rates that the building will actually use. They're not allowed to claim any savings for infiltration, so there's no incentives to design an airtight building, and you're not allowed to claim any credit for low flow fixtures. So frankly, in my opinion, the Ontario Building Code, I think as we can see here, really is not challenging enough for the industry and is really in no way helping us drive down our energy and carbon emissions. And so as a result, a lot of the industry is relying on some of these other standards like LEED, zero carbon building, TGS, to help actually drive down and achieve net zero carbon goals across the industry. And I wanted to take a moment just to look at TGS again, just as an example. Here's the performance targets for a high-rise MERB across different versions of TGS over the planned schedule. So 2018 was the first year, and 2030 is ideally when all new construction projects in Toronto should be net zero ready, essentially. So looking at some of our interior gains as an end use, such as lighting and plug loads, and some of our other lighter HVAC energy uses, such as fans and pumping energy, these don't really change too significantly across these different versions. There are some slight decreases, but this isn't really where the bulk of the changes that we would anticipate to occur within our energy profiles. Looking specifically at cooling, we actually see a bit of a cooling increase, partially due to a higher performing envelope that actually traps more heat inside. High performances enclosure limit heat movement, and it kind of works both ways. But also something that's actually not included here is how the impact of climate change would impact our cooling. And as we move into a warmer and warmer climate, our cooling energy, if anything, would just increase even more and more than expected. And where we would expect most of the changes to occur would be within the our gas-based uses. So our heating gas and our domestic hot water gas shrinking exponentially as we're not only decreasing the loads with low flow fixtures and a higher performing envelope, reduced infiltration and improved ventilation, heat recovery, but also eventually, as you can see here in the net zero ready design, the targets, let's call it, we've shifted entirely away from gas to 100% electric heating. And this is great not only for the carbon emissions, but also because heat pump technology works so much more efficiently than traditional gas-based systems. And so just a quick look at some different high performance standards. The first is not a standard itself, mostly just a concept, but just the idea of net zero, which I think personally by itself is a bit of a useless term. It really needs to be defined for what you're measuring. Net zero gets thrown around a lot, and it's really important to help characterize what you're talking about. I think some of the most common probably is net zero energy or net zero operational energy. So making sure you're producing as much as you are consuming, or maybe purchasing renewable energy credits or something like that. Probably the next most popular is net zero carbon, or again, net zero operational carbon. So looking at how much you're emitting on site, as well as through those scope 2 emissions through your connection to the electrical grid, and then offsetting that with carbon offsets or something similar. But then also there's the embodied carbon aspect that a lot of people are starting to consider more and more these days, which is how much carbon was used into the materials of your building, and would you be able to offset that? And then if you want to consider some combination of the two from your embodied carbon or your operational carbon, then you might be looking at lifetime carbon. There's also net zero waste and water, but that's not really specific to what we do as modeling. I just want to throw that out there. But yeah, and then beyond that also, not only just net zero, but also trying to consider net positive. So how can we move towards actually creating buildings that can generate good, or actively act as a huge carbon sink, if anything. LEED is probably the most popular standard in the GTHA as well as Canada, probably North America, truthfully. Version 5 is the newest, but version 4 is still in effect. And it's a very broad certification standard. It's a bit of a jack of all trades. It has a lot of different categories here, emphasizing many of the different aspects of building sustainability. The Toronto Green Standard, we've already spoken fairly extensively about this. Tier 1 just reflects your minimum requirements, but tier 2 and beyond are voluntary standards with financial incentives, and have also some different categories that, like LEED, kind of address different aspects of building sustainability. And then zero carbon building, which is a bit of a newer standard, but we're seeing it's rapidly gain popularity. There's a design and a performance standard. So the design standard is geared towards new construction, and the performance standard is geared more towards existing buildings and helping them electrify and, focus on have a very strong specific focus on reducing their operational and embodied carbon through retrofits. So I just wanted to do a quick walkthrough of a typical design process and maybe highlight some of the points where we use energy modeling as a tool. So at the pre-design, it's very, very early on in the project life. You're really just doing site analysis, maybe doing some goal setting, still trying to figure out exactly the kind of specific scope and size of your building or your project. Moving into the rezoning stage, this is when a lot of the building massing will get set. So a lot of your exterior, the form will be made, but a lot of the aesthetics and the look for the building exterior will still be kind of up in the air. Potentially, you'll have some very preliminary interior layouts at this point. But then when you move into your schematic design, that's where a lot more details will start to come in, especially related to the exterior of the building. You're starting to work on elevation details, starting to get a feel for your building materiality and the cladding, as well as on some of the interior side, mechanical and electrical may come in and do some very high level visioning. So kind of understanding what mechanical systems the team is most interested in exploring, which is great because at this point, which is typically, maybe at the site plan approval stage, is when we would require a Toronto Green Standard model or an SPA model. Other municipalities typically also require a site plan model as well, which at this point, as you can see, there's not a lot of real information to go on. No drawings have really been done except for just a few coordination architectural drawings at this point. So these models are built very heavily on just preliminary information, and a lot of it relies on the design vision, as well as assumptions from us as well as from the design team. Looking at the detailed design, this is when the project starts to get, as the name implies, significantly more detailed. We start to work on some architectural detailing. The unit layouts might start to be finished on the interior, as well as the mechanical team might have done some equipment selections. Then trying to take this and really advance the process along into the construction drawing stage. That's when the specifications get drawn up, schedules will be developed and finished, as well as a lot of the final detailing will be done from an architectural and mechanical perspective. And then using these completed construction drawings, that's when the team will head into permitting for official review. And we will actually have to develop our building code model at this point based on everything we've received up until this point. And sometimes the difference between the schematic model and the code model is quite extensive. This could be a few years of time in between, but also sometimes because of how the site plan approval works, it's very iterative. There will be multiple submissions. This might have occurred over and over again, maybe throughout the constructions drawing stage. Ideally not, but it does happen. And so sometimes these two models are maybe just a few months apart instead of a few years apart. After building code, after permitting is the tendering, which is unfortunately, I like to joke that this is when a lot of the value engineering occurs. And I was working on a project with somebody and they said that value engineering is the only engineering that actually matters on our project, because this is when they'll come in and double check with the costing to make sure what can actually be acquired and purchased for this site. And then when it can't be, I know, Bettina. And then when it can't be, what like appropriate substitutions can be made. And sometimes people have very different definitions of what they consider to be an appropriate substitution, because sometimes that just means, oh, we'll just get rid of all the insulation here, or like, oh, we'll just cut the insulation in this roof by whatever. Or if we had these great features that were saving us energy, but maybe it's not an absolute requirement, we'll cut these features. So a lot of changes can actually happen in the tendering stage, even though it occurs after the building code model has already been submitted. And then moving from tendering into the actual building construction, this is when there'll be a lot of site inspections and shop drawing reviews. And depending on the scope of the project, we may also be working on what's called a final design model, which would be required for some standards such as LEED and zero carbon building, that requires us to take the final design of the building and then use that information to develop an energy model to see if it achieves the requisite targets from that standard. And then we'll move into commissioning, which is an optional process, but I think something that's highly encouraged, and I believe is something that will be discussed also at bootcamp, which is essentially just a process by which you'll have a lot of your different mechanical, not just mechanical, but a lot of your mechanical, electrical, life safety systems assessed, make sure they were installed and operating properly. So come in and do testing, balancing, looking at the controls, making sure those are configured properly, as well as working with the building operator to actually train them and make sure that they'll understand how to effectively operate the building as intended. And then beyond that, we have occupancy, maybe a measurement and verification program if something is set in place. And then some standards such as Toronto Green Standard or LEED as well may require an as-built model. So actually using as-built drawings. And hopefully in the best case scenario, this model is very, very similar, if not the same as the design model, because hopefully nothing has actually really changed across the construction or commissioning phases. So this timeline represents maybe a fairly typical high-rise residential building, could be somewhere in the range of 5 to 9 years. And, you know, I've highlighted 4 different opportunities where we may have a model involved. But if a project is not performing any high performance certifications and is not located in a municipality with green development standards, then really the only model that's actually absolutely required is just the building code model. And I actually think this maybe occurs in the worst spot in the timeline, because it occurs a little bit too late to be able to have a really strong, really good influence on the building design. Like, it occurs much after the building massing has already been set, years and years too late. It's very challenging to actually change too much of the elevation details. You can't actually go in and change you can't go in and change most aspects, I should say, of the mechanical and electrical systems. You can really only do very light unit substitutions at this point, but the building code model also occurs before tendering. So we can say that the building will be doing all of these things, and then through the tendering process, potentially some of these might get value engineered out. And in reality, you're supposed to go back and update the model for subsequent submissions, but sometimes people just don't do that. And there's a lot of challenges with the industry of making sure you have good consistency and transparency with kind of like what you're submitting to building code and kind of what gets fully implemented at the end of the day. And so just some different examples of what I was talking about, some different interventions at these design stages. At the building permit stage, you may be able to just add a few inches of insulation to different wall assemblies, but this can be challenged by the size of the wall or risk of condensation. From a mechanical perspective, you can't really change much, but you might be able to purchase a more premium unit. So changing your unit selections, as well as maybe making some very slight alterations to your glass. But if we had the opportunity to work at the schematic stage, for instance, then we'll still always be having some challenges working with the design team, but these become much, much simpler. The possibility of maybe working with the architect to rework entirely what the building elevations look like, choosing different assemblies and different cladding materials for your building, exploring the feasibility of completely different mechanical systems. So instead of selecting something that is a very traditional gas-based system, maybe looking at air source VRF systems, geothermal systems, for instance, and then, you know, really adjusting your project goals as necessary at this point, finding something realistic, maybe being able to help stretch the design team to work towards something that they didn't necessarily think was possible. And then if we're engaged at the onset, at the get-go, we actually have the opportunity to advise even on the building massing. So which aspects help with shading, which help minimize heat loss across the enclosure. We can have some very early input on the project goals, as well as maybe help source and acquire financing as well, and then assess the feasibility of different site-specific measures. So like geothermal, which is not really favorable in tall buildings, or not as favorable, I should say. And so trying to wrap up here, energy modeling in design overall, it needs to be an integrated process. So really should emphasize early collaboration and use a lot of iterative feedback to impact your envelope and mechanical systems, working with the architect and mechanical and electrical design team, building scientists, geothermal consultants, everyone. And some best practice tips for anyone who might be interested in starting out at modeling. Start the modeling and start your strategy as soon as possible. So get in at pre-design or schematic when you can. Coordinate your work with all the disciplines. So making sure you're actually speaking to different design professionals on the team. Understand the targets. So know what you need to do for minimum compliance, but also what the different metrics and targets you're working towards for your various high performance voluntary standards. And always make sure that you document your assumptions and inputs clearly. A very common expression within modeling is garbage in, garbage out. So make sure that you're building up your model as properly as you can and documenting all of your inputs. And just some last key takeaways. Energy modeling best implemented early to be able to actually impact building design. So getting in at the schematic stage or earlier would be ideal. Building code kind of occurs, frankly, a little bit too late. It's very much just a compliance-based checklist at that point. Energy modeling is best considered as an iterative process where we have continued coordination with multiple disciplines across the entire team. So not just one-way communication, but constant loops of feedback. Relative and absolute performance targets that we've already discussed, they each have their own strengths and weaknesses. And depending on which ones will be required by which codes and standards you'll be referencing, they'll impact your modeling strategies and results differently. And last, figure out which targets and certifications are appropriate for your project. So we've already discussed this a lot, but not all these standards and codes are equal. So make sure you understand what is best in the best interest of your project team and try and work towards those. And thank you so much. I see that Samantha has been addressing some questions in the chat. I think we have a few minutes for questions now.
I'm just
believe,
gonna
right?
out loud finish my thought on this last question. Thanks, Michael, for that. So just the building massing, it's the size and shape of the building. Why that can matter is the loads of your building can vary greatly depending on what your building looks like. There's like a kind of joke in modeling world and engineering sometimes that the best designed building is just a square box with no windows. No one would want to be there, but that would be like the most energy efficient building that you could probably make. No one would enjoy it. But in terms of that, like if you think of like a square box, there's so much area that your heat loss or gains would happen through your envelope. But if you have really high ceilings and like a really complex shape, you could have the same amount of floor area being serviced, but you have a lot more thermal losses from everything. Additionally, the more like complex your massing is, so if a square versus like I think of like the Expo building in Montreal, it's like all these cubes stacked on top of each other. It gets more complicated to detail those buildings as well because you have so many different interactions for things, which can lead to more thermal losses. So you could have the exact same wall assemblies, details, mechanical equipment, same efficiencies, everything on two different buildings. And if one is a square box and one is super complicated, that one that's super complicated will use more energy. So, we want your building to be beautiful, but we do want to be mindful of the impacts that how you design your building will impact your usage as well. Cool. Any other questions for me or Michael? You want to learn about modeling or all of these very complicated standards we have to refer to?
I have a question. You showed in your presentation like the diagram of like the parametric modeling. I'm trying to learn more about parametric modeling myself. So I know there's like a bunch of different softwares and things like that, but what softwares do you guys use when you guys are conducting your parametric analysis and simulations?
We use Energy Plus as the main modeling engine. So
Yeah.
that's what we'll use for modeling. And because I think Samantha alluded to this, it's open source. So if you look up, there's all these great like resources and forums about kind of like how to help build and debug your Energy Plus model. And somebody out there developed an amazing tool, and I believe it's just JE plus. Plus is spelled out, and it's free software that essentially is exactly what we use to build this. It helps you iterate through um, thousands and thousands of different modeling parameters, or rather, I should say dozens of modeling parameters to give you thousands of outputs. And it's free. It works great. It's a little challenging to use because with any kind of open source tool, there's not necessarily a lot of instructions about it, but it's a great tool because it's very customizable and it's completely free, and Energy Plus is, one of the industry standards, so it works great from that sense. But yeah, there are other tools that exist, and yeah.
I'm trying to, so I use Grasshopper a lot, so I'm trying to get familiar with like Honeybee and Climate Studio. Have you guys heard of those? And are those relevant to the industry? Is it expected to know that kind of software?
We have heard of it. I will say, from my experience, it depends a little bit on your kind of like which setting you're in. So if you're in an architectural space with a focus on energy modeling, that tool would, I think, be extremely relevant. If you were in a more dedicated modeling firm, they tend to use, some of the software that we highlighted, like very dedicated energy modeling software. These plugins they're primarily more used in an architectural setting.
That
I
would
would
make
say
sense.
we do have someone on our team who does use Grasshopper to like start off some stuff. But then that's kind of like to build it up and set things up. Like most of our team uses SketchUp for that. He uses Grasshopper, but then exports it to Energy Plus to actually run the simulation and get more detailed, which that might be if you want to be more detailed modeling, a good way to look at that.
Like he exports the geometry itself, or can you export like your script?
So I know you can export the geometry. In terms of detail, he does do some detail at that part. It's I'm not familiar with his workflow entirely. I just know you can do it. It's for Energy Plus is very open to letting you do what you want to do. Like we've written Python scripts that help transform Excel spreadsheets into like setting up our mechanical systems for us. So there's a lot you can do with it. I don't specifically know the details of what you can export from Grasshopper, but quite a bit.
A little bit too nerdy for us. Not too nerdy like it's not too nerdy like we don't know it. Other smarter people on our team set up these great tools for us.
Okay. Would it be possible if I could have the contact for your colleague, and maybe I could talk to him about this further? Maybe grab a coffee with him.
I think you have our contact. Send it to me in the chat. I'll pass it along because I don't know if he's okay with me sharing it. I think he will be. He's pretty big on nerding out on things, but yes. But oh, sorry, we're on break. We're cutting into your time a little bit, but I see in the chat someone wants to know a reliable resource for learning Energy Plus or IES. I will say for IES, because it's a proprietary software, you have to pay for it. I think they have some internal training things that you can do. There are some courses that are offered sometimes. I know one of our colleagues sometimes offers one. Other than that, because Energy Plus is open source, there's a lot of just stuff online. Like you can look on YouTube. There's a lot of great sites. There's one website called Unmet Hours that is just full of energy modeling questions and help navigating things. It's like an open forum. Michael, do you have anything else you can think of?
Yeah, I was gonna say earlier we talked about Open Studio, which in itself is not modeling software. It kind of is just it's a interface plugin with like SketchUp and all this stuff, and they rely on Energy Plus as well. But Open Studio, also great free resource, has tons of resources about how to learn to use Open Studio modeling, which functionally is just Energy Plus modeling. It just kind of looks different, but because they use the same engine, it's all of the same processes. And I'll be sharing with Bettina our slides, and at the back half are some resources, including, it's called the Open Studio Coalition. And this is kind of like, it's just like a great free resource about learning how to use Open Studio as a modeling tool. And then within that, they kind of implicitly teach people how to use Energy Plus. I will say I haven't used it, so I can't vouch for the quality of the structure and the lessons, but I flipped through it and it seems great and really extensive.
In a general sense, what's the difference between Energy Plus and IES? I would say IES is more of a package deal, like because it it's a product, they're selling it. It's a little bit more visual, so you can like build up like, hey, this is my boiler, it's connecting to this pump, so you can kind of like see what's happening a little bit better. In terms of like the results you get out of it, I think the results are pretty similar. Energy Plus can be a bit more non-intuitive because it doesn't have a visual component to it. It's basically just a list of different things. Like, Michael, I don't know if you can quickly pull up a model and just show what that looks like. It's not easy to navigate. But the benefits that you get from Energy Plus are just how open it is. Because like IES, if you are having a problem with something, you have to like contact them, wait for them to answer you, see if they can give you results, and you kind of have to work with the toolbox they give you. Energy Plus, you can really do anything you want. You can connect anything you want. You can build whatever you want. It has more flexibility. It's a little harder, I think, to get in the door, but it is free and is personable. Something that helps with that is Open Studio. So Open Studio, Michael was saying, runs on Energy Plus, but it does have a visual component to it. It's kind of like a front end for it. So it can give you a bit of that, a little bit more of a sense. Yeah, this is what Energy Plus looks like. It's just like these are all your cooling
It's just a
coils.
huge walls of text. That's all it is.
Yeah. And they like link together. There is like a template mode that you build first that like is a little simpler, and then you expand it to go into more detail. You don't have to expand it. You can just go based on the earlier thing. It's a little less detailed, but like we use SketchUp to draw out our models because sometimes otherwise you would have to be manually writing in all these points. There's a lot of different tools out there that connect into Energy Plus that can help. Like Open Studio is one that you mentioned, but there are some other front ends as well. I can't remember the names of any of them right now, but there are other tools as well. Ooh. Yeah, Energy Plus here with Rhino and Grasshopper for parametric modeling and building geometry. Yeah, there's like Grasshopper and Rhino definitely can tie into Energy Plus more. It's just not something I'm as familiar with, but there's a lot of stuff that plugs into Energy Plus, which is part of why it's a little bit more appealing to most of the market. There's a lot of the industry still uses eQuest as well. If you want to just get your foot in the door modeling at all, eQuest is great. It's also free. It's a little easier to get in. It has like a front end interface. It has like some menus to help set things up. Its limitations is that it's a little bit of an older software. Like the Department of Energy shifted from Energy Plus from eQuest onto Energy Plus. So what mechanical systems you can do, sometimes you have to do kind of like workarounds, but if you just want like a basic building and just kind of like get familiar with what's there. Also a great option.
Awesome.
I will say, Energy Plus is mostly the last point. Energy Plus is very academic. And IES tends to skew more industry. So it's not to say both don't occur in either space, but a lot of the people that use Energy Plus are in kind of like these like research-based fields because, like Samantha's saying, it's very customizable. It's very open, very huge community of like different academics, especially kind of using it to like model very niche scenarios for like research.
Amazing. Thanks, guys. Always such a great presentation. We deeply appreciate it so much. Sharing your open and honest.
Send us an email. We'll be around Thursday during the workshop, and we'll be there Friday as well to hear all your presentations.
Okay,
Yeah.
thank you so much.
And if people prefer
Go
to,
ahead.
they can like find me on like LinkedIn or something and message me there
Yep,
too.
so
That's
we've
fine too.
invited you to our LinkedIn group so that you can join us there as
Oh,
well.
okay, great. I'll do that. Perfect.
Excellent.
Awesome.
And if you
Thank you
could
so
please
much.
send us your presentation so we can share it with the students later in the bootcamp.
I will do that today. Yes.
Thank you.
Thanks, Michael. All right, guys, see you soon.
Thanks, everyone.
Bye-bye. Thanks for
Bye.
having us.
Hi, Nicole.
Hello, good morning. Hello, Nicole.
Hello.
My name is Oye Kiloman, and I have the pleasure of introducing Nicole to the house. Nicole Pearson is a WSF, first call specialist in the building science group in SPS Toronto office with a focus on new construction and a deep retrofit. She enjoys seeing her project through from conception to completion, including a problem solving involving with working through challenging detailing to ensure the client is receiving the quality they expect. Nicole believes a successful project is in depth of effective communication between all teams member, the consultant, the contractor, and the owner. Nicole has worked in SPS, Toronto, Calgary, and Hamilton office. Nicole, it's your time.
Thank you. Morning, everyone. As you heard, I am with WSP in our Toronto office. I know that people here are from across the country. I am starting with a picture of Toronto because that is where I am, and the kind of ongoing theme of my presentation is going to be I'm kind of tying it back to the concept of making sure that you can see the forest for the trees. And this is our urban forest here in Toronto. So overall, big picture thinking. So I'm going to be talking about commissioning as well as operations and maintenance of buildings, and really how that ties into considerations during the initial design and construction process in a big way. So like I said, commissioning is about taking a step back so you can see the entire forest. Every individual designer and individual person or team working on a project tends to have a very focused mandate, and you can get kind of lost in that tunnel vision. So commissioning, we're taking a step back, we're adding a second set of, or another set of eyes, another layer of review. It makes me think of a few months ago when I was writing a report for a client. These days, I don't write a lot of reports myself from scratch. Usually others on the team write them, and I will review and comment and edit before they're issued. But a few months ago, I was writing a report from scratch all on my own, and I was finished, and I was confident with the technical information that I was providing. I was confident with my conclusions and my recommendations, but I also knew that I had been, head down, buried in this report for 2 weeks, and there were likely things in it that I wasn't seeing clearly because I was too close to it. So I had a colleague have a look at it for me to get that bigger picture. And that's the same idea of what commissioning is. It's a separate team, separate people from the design team, quality-based process, and it can be applied to absolutely any project. There are governing standards that are out there depending on the project, whether or not there's any specific certification, such as the lead commissioning requirements, or potentially other entities, like government entities, may have specific commissioning standards that they want to be followed that are specified as part of the project. But really, all of them kind of boil down to determining what is important for the project and how is that being checked and verified. So a lot of times commissioning is thought of as testing. You test the mechanical and electrical systems, you test the concrete, the sealant, the membranes, you do water testing, air testing for the building enclosure, and that is a component of commissioning. It's an important component of commissioning because you're verifying the performance of those assemblies and components of the building. But commissioning is an important part of the entire design and construction process, starting from the pre-design phase all the way through to building startup. And then at the time of building startup, the intention is that the commissioning process has laid the framework and put in place all of the information needed for optimal and efficient operation and maintenance of that building. So in pre-design, you're defining that what's important for that project. What is the basis of design? You're starting your plans. As it goes through the design process, the commissioning targets, as well as how they're going to be verified, starting to put together, requirements of manuals, all of that is progressive throughout the project. And then, of course, as you get into the construction phase, you get into actually checking and testing and verifying and reviewing all of those kinds of quote unquote typical, what is thought of as typical commissioning. So having that commissioning involvement early is important because the earlier you are in a project life cycle, the easier and cheaper it is to impact change to that design. The farther down the road you get, the less change that is possible without, completely redoing everything starting from the beginning. And the cost of any of those changes starts increasing significantly as well. The other kind of benefit of early involvement, or the other process that also helps contribute to that, is the integrated project delivery effort, which I am sure you're hearing from other people this week. And that allows, so that the integrated project delivery and commissioning very much go hand in hand. And it's about bringing teams together, early involvement, checks and balances, all of that kind of stuff. And another way to think about a similar kind of concept is that during the execution, so the design and construction of a building, about 80% of the life cycle cost is determined during that time based on decisions that are made during that design and construction stage of the building's life cycle. But 80% is incurred during operation. So it's important to have that holistic view early and to be taking into account the entire building life during those early stages to really optimize the full life cycle of the building. And this ties back to what I was saying a couple slides ago about integrated solutions and commissioning being an important part of that, along with the rest of the design team and specialist consultants and the owner and the constructor and the operator and all of those good things. So one thing, commissioning is becoming more and more common in the industry. It's something that more owners and developers are requiring. It is something that some people may be thinking, well, we have lots of buildings that are quite durable that were built 50 years ago. Why is this, what happened? Why is this now something that we're really starting to focus more on? And there are a couple of reasons for that. The first is the complexity. The complexity of buildings has increased significantly. There are a lot more things to consider than there used to be. There are a lot more different ways of constructing buildings than there used to be. So as things get more complex, there is more risk and more chance for error. There's increasing demand for high performance buildings. Codes are demanding it. Building owners are demanding it. Just industry and the world in general is demanding it. We need to improve building performance. We need to reduce energy use. And then you're getting into a situation where your HVAC systems and your building enclosures are interdependent in order to optimize and achieve a high performance building. Also, like I said, we're incorporating more innovative assemblies and materials. Assemblies are becoming more complex. So with all of this increasing complexity, increasing demand for performance, we have to mitigate the risks of that additional complexity. We're also thinking about future ready. So we're talking about increasing temperatures, increasing water levels, more flooding, more disruptive storms. What we are designing buildings for today, they will need to survive and perform through extremes that existing buildings, many have never seen. We're talking about all of these more extreme conditions and how that's managed and mitigated. And it's not only the extremes, it's the sudden shifts. So it's the temperature swings, right? It's 40 plus with humidity, and then all of a sudden 2 days later it's 15 degrees, which is something that in Southern Ontario we've lived through in the past week. It's something that anyone that's in Calgary, it would be very familiar with in the opposite way, with Chinooks in the wintertime and those big temperature swings that those bring. So all of these things impact the mechanical systems, the electrical systems, the building enclosure, and have to be taken into account, and the way that all of those things work together. We're also talking about resilience of buildings and resilience of the systems in those buildings, the ability to absorb those shock events and adapt and recover quickly. And again, that's those storms and the flooding, potential power losses becoming more common as weather extremes become more extreme. And then to tie back to what I was saying earlier in the presentation, the more complex the building is, obviously the more chance there is for risk. Also, the bigger impact commissioning has on the building. So in terms of lowering that risk level, there are benefits for commissioning on fairly simple projects as well, but the scale of that risk reduction really is most widely seen on the more complex end of projects. So as we move in that direction, commissioning becomes, it's just more of a no-brainer. The benefit versus cost balance just works out in the favor of the building. So to look at, I'm not going to spend too much time on this slide because there's a lot of text here, but this is a commissioning plan outline for building enclosure commissioning. As you heard at the beginning of the presentation, I am a building enclosure specialist. I am trying to keep this presentation, not too building enclosure centric, but this is an example of an outline of all of the things that we do as part of building enclosure commissioning. The M&E commissioning graphic would be even more complex because there are, of course, more systems. There are more different systems, and there's a lot more startup testing and verification for those systems. the testing for the enclosure tends to be a little bit more straightforward. Still very important, still needs to be done. The testing for the enclosure often is one of the first things to get dropped if they're trying to save money. But just because it's kind of a quote unquote easier test doesn't mean that it provides less value. It's all very important. Commissioning, I've been talking about, with a kind of a new construction point of view. I've talked about design and construction and commissioning and turning over a building. But there's also retro commissioning and existing building commissioning. And that can be as part of retrofits or major work happening at an existing building. But it can also just be looking at an existing building and checking and verifying and optimizing performance. It can include energy modeling and energy auditing, energy improvements, facility condition assessments and surveys. All of that kind of ties into commissioning. So with that said, how, we've talked about, and I think a lot of people are probably aware of the importance of building a good building. We want to build what was designed, meet the owner's performance requirements, not have one thing on the drawing, then something else completely different end up being built. But how does this tie into longer term building life, operations and maintenance, and those sorts of things? So early planning for operations and maintenance. And so these are things that we're taking into account, again, during the design phase of the building, but thinking long term, farther ahead. So it's things like layouts of service rooms. It's clearance around equipment, the ability to open access doors to safely access the equipment. These are all interior photos, but the same kind of concept applies on a roof. If that image in the top left was a mechanical piece of mechanical equipment on a roof, then you're, here we're saying minimum of 1 meter from the walls for proper access. On a roof, we're saying more than 6 feet back from the edge of the roof, because you want to avoid a situation where somebody who's needing to go out on the roof to check a piece of equipment has to put on fall arrest equipment. Because quite frankly, most of the time it's not going to happen. If somebody just needs to run out there quickly, they're just going to run out there quickly, and you don't want that machine to be positioned so that person's putting themselves at risk. So it's about setbacks and proper barricades and all of those kinds of things to make sure that maintenance can be carried out properly, safely, efficiently while the building is in operation. And then kind of tied to that roof thing is exterior access. How are people going to access the roof for maintenance reasons, the walls for maintenance and cleaning reasons? Yes, for large portions of a building's life, the outside walls are probably only going to be accessed twice a year for window washing. But when there is the need for repair and renewal, how will that happen? How will that access be achieved? Even if the full access system, like on a high rise in a downtown, with maybe a permanent access stage on the roof, even if that access stage is not going to be necessarily installed as part of original construction, the building itself has to be designed in order to accommodate that, knowing that that will be required for future maintenance work. Those kinds of considerations. Then also, small, quote unquote, smaller scale things, maintenance, repairs, concealed conditions, how are people going to be able to access different parts of the building for not one-off, but to address any issues? If you have high risk, joints in your building enclosure, or high risk detailing that is being completed and then will be blocked by structure, maybe it's being built from the outside, but then once it's built, if you need to access it for repair, that you have to access it from the inside, but you have giant structure in front of it. Taking that stuff into account, thinking about how often and how extensively these areas need to be accessed, and planning for all of that. Very important part of the upfront design of a building. Things like and there will be times where there are non-accessible components of a building. This is an insulated metal panel. The panel joints have concealed sealant in them, where those red marks and arrows are. The panels are put up progressively. There's no way to get into retrofit that sealant after the fact. That said, this product has its place. It can be fantastic. It used in the right way and in the right place, but it still needs to be considered as to, well, what are you going to do in the future if you have to address air leaks or water leaks? So one of the possible approaches, as an example, for this kind of an assembly would be, okay, well, if there is a localized issue in the future, or X years from now, when there needs to be a larger repair intervention or whatever the case may be, maybe the plan is at that time you go in and put membrane or sealant on the inside backside of those panels. And if those panels are concealed behind some kind of interior finish, then it has no aesthetic impact on the interior space, but you still have to consider that you have to get at those joints. So is that going to require removing interior finishes? Is it going to require some other kind of access? And a little bit further in the presentation, I have a few slides talking about coordination of maintenance activities and the importance of considering that early on as well. And then we're talking about these concealed conditions, difficult to access conditions, all of this kind of stuff. And we can't forget the visible conditions, right? We don't want to be so focused on these challenging and more complex situations that we just forget about the quote unquote simpler or easier to access things. All of this kind of stuff, like sealant replacements. This is sealant between precast cladding panels. Needs to be taken into account. Precast can have a lot of sealant joints. And again, that's not saying that precast is bad. Precast is actually becoming very favored in the Toronto market right now. It is, and for speed of construction, upfront cost of construction, the ability to achieve good thermal resistance of the enclosure, durability of the enclosure, all of these kinds of things. There are a lot of good things to say about it, but we still need to take into account the fact that there is a lot of sealant that needs to be factored into the plan. And something as simple as the the type or kind of sealant that is used in those joints initially can have a significant impact on the lifespan of that sealant. So making sure that all of these things are thought of and taken into account. And then even simple, tiny little things, this is an aerator off a faucet that is all gunked up. But when we're, as part of the commissioning process and setting up this building for success and putting together these systems, operations, and maintenance manuals, having all of these things to consider included in those manuals so that the building operators can use those manuals to run the building day to day. And if there are things that they, should be checking every month, every 2 months, every 3 months, etc., every year, every 2 years, what have you, having all of that outlined and summarized and all of that kind of stuff, so that there's a roadmap to running these buildings efficiently. On a larger scale than an aerator on a faucet is roofs, and annual maintenance and review of roofs. Lots of times this is something that can be included in the original contract from the roofer who installed the roof. Sometimes it's a requirement of some extended warranties from manufacturers that that's included in the contract. Sometimes it's something that the building operations staff themselves are able to do, depending on their level of knowledge and background and expertise. But it's the kind of thing that if you just leave it and forget it, by the time you realize there's a problem, it's going to be a very big problem. And we want to be having processes in place to identify problems early before they get out of hand. So that brings us to the maintenance cycle. And this is kind of what would probably be considered a typical maintenance cycle. So we design, we construct, we have our testing, quality assurance, quality control during the construction. We have the commissioning that occurs, as I said, both during design and construction, but then also as part of handover, warranty, dispute resolution, deficiency repair, that kind of stuff. Now the building users have taken over. Hopefully they have some kind of capital planning, business planning process in place, and you repair localized problems. At some point you restore the building, which is, larger scale repairs. At some point you get to the point where you renew the building, upgrade it or reposition it. It's a cyclical, you design and you construct. But there are a lot of things to consider, and this kind of goes back to what I was saying about aligning different maintenance schedules and replacement schedules. So this is the traditional approach to building repair and renewal, right? We have the HVAC, central plant and equipment, expected service life, the ductwork, the glass in the windows, the window frames themselves, sealants, cladding, roofs. It's always a range, but you have an expected service life, and the traditional approach is you plan to replace or completely overhaul a system at the end of its service life. As you get closer to the end of its service life, you anticipate that there will be additional maintenance costs that will come up, kind of, so you can stretch out that service life, and then you kind of start all over again once you get to the point of having to replace it. But that's not the only way to approach building repair and renewal. And as we think about not only minimizing long-term costs, but also when we think about carbon costs as well. So not only monetary costs, but carbon costs. We don't want to be removing and throwing out and getting rid of components or portions of a building which can still be used, right? We don't want to be sending this stuff to landfill and bringing in new components, because the embodied carbon cost of that is astronomical. It's so we're so looking at ways to maintain systems to extend their service life, to have larger interventions earlier, which can avoid or significantly push out that really big intervention. So this is an example for conventional roofing, where you start and the condition is excellent, and the blue line that follows the green, orange, and red sections under the graph, over time, the quality of that roof, due to aging and exposure, drops off. And then at a certain point, this graph is showing after 30 years, you get to the point where you're going to have to do a full replacement. The estimated cost at the time that this graph was put together was $45 a square foot for full replacement. Roofing costs is fairly volatile because of the all of the stuff with tariffs, and a lot of roofing still uses petrochemicals and the varying costs of the materials and all of that kind of stuff. But not to get bogged down in that, there are options. So if at 15 years, that's the blue line that goes up here, you can do a resurfacing. So if it's a product that you can resurface, and again, that is something to be considered during the design, and you resurface at 15 years and $25 a square foot-ish. And then again at 30 years you resurface, and then again at 45 years you can resurface, and it allows you to avoid having to tear off that entire roof system. You are renewing it by resurfacing it. You are putting in smaller amounts of money spread throughout its service life to get a longer service life. There's also, if you miss that first window, you can put in a larger amount to renew it. You can have larger investments spread further apart, but still avoiding that full replacement. So the green line, instead of resurfacing, maybe it's removing the membrane and replacing the membrane, but leaving the other components in place, because you've done that intervention before there are widespread leaks. So your insulation is still all dry and in good shape. So you can replace the membrane without having to replace all the insulation below it, as an example. So looking at these types of non-traditional approaches to maintenance in order to optimize both the longevity of assemblies, but also the life cycle cost of those assemblies. It is, from a monetary point of view and also a carbon point of view, is important, and is something that is becoming more important as we are becoming more aware and focused on mitigating our impact on the environment and on the world around us. In addition to that, taking that traditional maintenance cycle that we looked at and applying it on a full building scale. So on the left, we have that design, construct, commission, warranty, repair, and then restore and back into that design, construct, commission, warranty, repair, restore cycle for a repositioned and building 2.0. So taking into account how that, of course, we don't know what use society is going to deem most important for a given building 50 years from now, but taking into account how a building may be repurposed and repositioned, looking and putting together systems that can support that approach without having to be completely removed and replaced, taking into account the fact that a building will likely have many lives in terms of its purpose. It will have many purposes throughout its many lives. And then another component of that, which ties into what I was saying earlier, is the future approach to holistic renewal. So we have that graph there on the side that I showed you earlier with the different service lives for some different components. On the right, it is looking, and this is looking at a historic building that was built in the 80s. This slide came from a presentation on building retrofit, but the same principles apply to a building that is being built today as well, or a building that is being retrofitted today and then looking forward to future maintenance after that retrofit. So you have different components, different timing for their expected service life, different levels of cost depending on what that component is. And looking at those and kind of lining up where items, components, assemblies are going to be all approaching the need for renewal at about within a given time window, it gives you that chance for holistic renewal. So it gives you an opportunity to plan that the HVAC equipment will need to be replaced, and the windows will need to be replaced, and the cladding will need extensive repairs, and the sealants will need to be replaced, and the roof will need to be either repaired or replaced. And that allows identifying that and putting together a maintenance plan for the building that takes that into account, sets up the future operations and maintenance of the building for success and for the opportunity to make further holistic improvements to that building when this time comes. Because the other risk is you get over here in 2050, for example, and think, oh, I would have loved to have done that holistic, but I just replaced my HVAC 5 years ago, and my windows were 10 years ago, and the frames, I don't need to replace those for another 30 years. But if I had done X, Y, Z at that time, then I could do something different now, and I would be able to save all of this carbon emissions and money, and my tenants would be more comfortable, and whatever the case may be. So setting up in the long-term operation and maintenance plan for the building, those opportunities and having those identified so that the building can be operated and maintained with that in mind, so that those opportunities are not missed, because they really are like a once in a 40-year kind of opportunity. And if you miss it, then either the renewal is not going to have as big of an impact as it could have, and or it's going to cost significantly more, and or be more wasteful because you're redoing things that don't necessarily, that shouldn't need to be redone because they were only renewed very recently. All of that to say, plan ahead of that and identify that. Before I finish up and start taking some questions and discussion, I have a case study that I want to show that kind of show, well, it shows the importance of commissioning and having that process during construction, and also of holistic thinking. So the background of this. So this is a new MERB rental in Eastern Canada in the Atlantic provinces. There were multiple challenges during construction with the window wall installation and with resulting water leaks as a result of issues with the window wall installation. The issues of this case study came up during the first winter of occupancy, so the first winter of tenants living in the building. And there were reports of excessive water inside the suites at and near the windows. So a little bit, concerning initially, especially given that there was history of installation issues with the window wall here. So one of my colleagues went out to the site, and these are some photos that she took. The top left one is taken in the top top corner of a window. You can see that there are a lot of droplets of water along the top, and on the bottom right, you can see the reflection along the windowsill of the dark frame. That is water. That entire ledge of that frame is wet. There's so much water there that it was spilling over behind the wooden sill and ending up on the concrete slab, which is why the flooring adjacent that window has been removed because it was wet and lifting. So they cut it out to try to figure out what was going on. So we're talking about excessive volumes of water here. So what did we observe? 45 to 54% relative humidity in the suites, which is extremely high. For occupant comfort, relative humidity should be between 30 and 60%. However, in order to avoid and minimize risks of mold growth, relative humidity inside dwelling units should be kept below 50%. And in the winter in Canada, during extreme cold weather, typically we're looking at between 30 and 35% to avoid condensation on window surfaces when you have aluminum framed window systems. It's a limitation of the system. It kind of is what it is what it is, for lack of a better description. If some window systems will have a higher surface temperature and be able to accommodate a higher relative humidity, but as the RH goes up and the dew point of the inside air goes up, the risk of condensation goes up. So for a multi-unit residential building with aluminum framed double glazed windows, 45 to 54% RH in the units is very high. In-suite temperatures were 21 Celsius and above, which is fairly normal, but that was relevant because the in-suite HVAC systems were not running. They were hardly ever cutting in. Some of the tenants had standalone dehumidifiers that property management had provided. There's one in the photo showing the 54% RH. Because the in-suite systems were not cutting in, they weren't running. The corridors were very warm, so there was suspected passive heating of, when I say the units, I mean the suites, from the corridors. And as part of this review, the M&E designer insisted that the issues were not related to the M&E systems. They absolutely must be related to the windows. The windows must be leaking in the middle of the winter when it was -20 outside. Windows don't leak when it's -20 because there's no water outside to get in, right? Even if there's moisture, it's snow. So generally windows don't leak when it's -20, but this is kind of where we were at this point in this process. So we looked at, okay, well, what might our recommendations be, all while taking into account that we were the building envelope consultants on this project. We were not commissioning agents. We had no involvement in mechanical, electrical. There was actually no commissioning agent on the project. And so we needed to stay in our lane and deviate only as much as we could without causing upset. And this is the kind of thing that if it was a project that had a true integrated project delivery approach, which it did not, that wouldn't have been such a challenge because the team would have had an established collaborative working relationship. And as it was, we were more like ships passing in the night. So we had to be very cautious of how we approach this and not get everyone's backs up. So the recommendations that we were working to put together were to evaluate the HVAC systems to ensure proper installation and set points. We specifically worded that to avoid angering the mechanical electrical engineer who was very adamant that it cannot be his systems. Consider reducing the corridor set points to quote unquote force the units or the suites to run their in-suite heat pumps. Even if you intended the corridors to be this warm, maybe dial it back, force people to turn their units on, and then that'll help pull down the RH some. Educate tenants on reducing RH in their spaces, i.e. running exhaust fans more often. This was something that was occurring in many suites. So it wasn't, we run into cases, right, where there's somebody who they just really like it to be nice and warm and moist in their suite, and they're running a humidifier in the winter and it's 60% RH. And but this wasn't that kind of, this was fairly widespread. So, tenant education always helps, but again, we weren't super optimistic that was going to have a big impact. So we were working on putting together these recommendations, and then before we could send anything out, we got an email from the client, and the email from the client said, "On the supply air wall box, the flap was still installed, preventing air from reaching the heating system. Today we opened up one with the M&E engineer and found that the airflow from the ERV was inadequate. This led us to check the supply air wall box, where we saw that the flap was still in place." This is a flap that is temporarily in place at the time of supply of the equipment to prevent dirt, debris, construction dust, all of that stuff from getting into the equipment units while they're being installed, before they're fully ducted, that kind of thing. It needs to be removed in order for the system to work properly. It was not. It was a widespread thing that was missed, and they went through suite by suite and removed those. Some of the suites it was removed, some of it wasn't. That's why not every suite was having condensation issues, but a large portion of them were. And after that, our recommendations changed to, okay, great, monitor it, and if there are still issues, let us know. And there were no more issues. Everything is running properly. But this is an example of, if a proper commissioning process had been in place, one, there would have been an additional set of eyes reviewing the installation, because the commissioning agent would have had someone there reviewing it in addition to the designer. And two, there would have been testing. The volume of airflow from those units would have, one of the tests would be to measure the volume of airflow from those units, to check the temperature output, those kinds of things. Not all of the units, but a good selection of them, to ensure that they were running as they were intended to. And this issue could have been identified and fixed before tenants moved in. They could have avoided the interruption to the tenants. They could have avoided having to, send flooring to the landfill that got damaged by water and having to replace it, both flooring and drywall. And in this case, the impact was relatively small, in the sense that, this wasn't $100,000 issue or anything, but it just highlights how easy it is to miss this kind of stuff, and how important it is to have those checks and balances in place. And that's the end of my presentation, but happy to take any questions, any discussion points anyone wants to talk about.
Thanks, Nicole. There's been a ton of chatter, and I'm just going to let the students unmute and go ahead and ask any questions. I will ask one. Annie is asking, is a holistic renewal plan required as an important requirement before a building is commissioned?
So it's not a requirement. There is, as far as I know, there are no standards or codes that require that kind of holistic renewal plan. It is something that is, it's still, I would still consider it progressive thinking at this point in time. But it's important, and as part of kind of being on the leading edge, it's an important thing to consider. It is something that some government entities are starting to think about. They are starting to write some requirements into their specifications and owner project requirements when they're tendering projects, but it's definitely not like a widespread requirement or a general requirement.
Yeah, I mean, definitely from what I'm seeing, everybody understands how important commissioning is now and how it's simply ignored. And my favorite part about your talk is this idea of, having to stay in your lane. Integrated design means your commissioning agent is involved from the beginning to help you understand. Yeah. And not, it is hard for professionals, if you're a mechanical engineer, it's your stamp on the drawings. And so to be questioned, you have to do it very, very delicately, or the architect or whoever the expert is. But if we work collaboratively and we start from the beginning to say, hey, I'm thinking about this design, what issues you in your experience as an experienced commissioning, because at our last boot camp, we had somebody just give example after example after example of building failures. She works for an investigative firm that works for the insurance companies to determine blame and money being spent there rather than at the design stages using lessons learned.
Yeah. And that's when you have that relationship, like, because you have the integrated process, you can have those discussions easier when something goes wrong, and it's much less likely that people are going to get their backs up and think that they're being blamed, because you know each other, you've been working together. At that building example that I showed, we had never even spoken to the mechanical electrical designer on that project. My colleague who is based out east and was on site regularly throughout the construction was the one that was there doing the review. She had never crossed paths with him because there was no integrated approach. There was never a project meeting that required both of them to attend, so they didn't know each other.
Yeah, it's tough. It's really tough. Oh my goodness. Okay.
Sophia asked, commissioning is so important. Do most buildings usually have their own dedicated commissioner, or do they usually outsource this service when needed? So the commissioning during the design and construction is usually an independent or separate entity. It is someone that is hired by and working on behalf of the owner to help look out for the owner's best interest. Some developers who may have people in-house who do that, but they also hire out because they hire firms who that is what they do, that is what they specialize in, and they can kind of give that little bit of an outside perspective versus somebody who is working for the development company and maybe has different pressures on them from the powers that be within the development company. So it's about balancing kind of different expectations. But in terms of operations and maintenance and the ongoing aspect, a lot of the larger companies that run buildings, that's in-house, like universities or post-secondary institutions, large commercial development companies that own buildings in downtown and shopping malls and all of that kind of stuff. Their operations and maintenance staff and the ongoing work while the building's in operation, those people are usually in-house. Sometimes smaller companies may hire an operations company if they're not large enough to have that expertise in-house, but in terms of the ongoing operations, that's usually in-house for larger companies.
Great question. Anybody else?
Thank you so much for a great presentation. I really learned a lot. Thank you so much for sharing all those stuff. And the question that I have, it was, is there any way to detect any issue on the building, or are you using a software, or are you using any any tools to detect what's the problem or what's the issue. That's the building right now it has. And so, yes, thank you so much for answering this question as well.
Yeah, so there are a number of different kinds of equipment and ASTM test standards for testing different kinds of concerns. So from a building envelope point of view, there are test methods where you use air and or water to try to identify leakage paths through the enclosure. You can pressurize a building so that the pressure inside is greater than the pressure outside. Then you can use an infrared camera to look for warm spots on the outside of the building, which can then be used to help determine whether there might be inconsistencies or issues with the insulation, or whether there might be air leaks, breaches in the air barrier or water control layer. From a mechanical, electrical point of view, like I mentioned, they would check the airflow. So they would check the volume of airflow that's moving through units and the temperature of the air going in and out of those units to make sure that it's within parameters. They can also check, they can take air samples and actually check them for particulates and air quality to make sure that the indoor air quality is adequate and that it's not being contaminated by something somewhere along the way. They can check flow of water fixtures. And so those are larger scale. There are also smaller scale tests for the enclosure. We can do sealant adhesion tests, membrane adhesion tests. There's a lot that can be done. And if you're talking about the existing building and kind of figuring out the issues, that would be a combination of visual review by people who are trained and experienced in those areas, and also potentially testing. Air tightness testing of existing buildings can be really, really beneficial because it can really help you identify where there might be issues with the enclosure, where that air leakage is occurring, and help you kind of target any repairs in a smart and efficient way so that you get the best bang for your investment, both, again, and when I say investment, I mean both money and carbon. Can the commissioning be applied to buildings that are already in operation? Absolutely, it can. That's the retro commissioning that I mentioned on the one slide. So you don't even have to be doing a full retrofit. You can you can have someone come into an existing building and do a retro commissioning where they look at all the systems, they look at the design documents that are available from original construction, and they will evaluate and look and determine if the systems are operating as they were intended to, and also make recommendations for tweaks or adjustments that could be made to make the systems more efficient in terms of energy use, but also in terms of optimizing occupant comfort and making the people in the building happier. And I see that there is a question about a course or a workshop to go through and learn more about it. There are building commissioning courses that are available through the Building Commissioning Association, I think it's called. The association is referenced on one of my slides, and they do have courses on commissioning that are available.
Thank you, Nicole. Just to add to that, do you necessarily have to be an engineer or like someone in the building community to be able to like learn those courses, or you can just take it as a niche and maybe work around it and maybe, let's say, start a company just on commissioning buildings or something like that?
Yeah, so there are companies that is all they do is commissioning. They don't do they might not do design, they just do commissioning. Within our team at WSP, we have a team that all they do is commissioning. The people on that team don't work in the design portion of our business. They just do commissioning. That said, there is a need for knowledge about the systems. So while you don't necessarily have to have an engineering background or an engineering degree, you would have to find and source and complete courses and or work experience to give you the background knowledge on the systems that are being commissioned.
Amazing. Thank you. I don't know if you are able and or interested, Nicole, but what we have now is what we call a coffee chat, which is where we stop giving presentations and we just talk about things like, how did you get into your career? And those sorts of questions. Do you have a few minutes to stick around? And
yeah, absolutely. Yeah,
that would be great. So yeah, students, turn on your cameras and like, this is the honest, just like, what did you study? Or, how important is a LinkedIn profile? Whatever you want to ask.
Hi.
Sebastian, go.
So I just want to ask with the Nicole that you said you were working with instruments and your team is just working for the commissioning. So how did you pursue this career, or you were apart from this career from the beginning when you started like your career?
Yeah, so at WSP, I'm not on the dedicated commissioning team. I am on our building facades team. So I do building enclosure commissioning. I also do building enclosure consulting, working with architects. I focus mostly on new construction buildings and or large scale retrofits of existing. So I don't get in as much to the smaller scale repairs of existing buildings, although we do have people who do that. My background, I have a degree in civil engineering from McMaster University. I focused on the structural stream when I did my degree, and right out of school, I started working for a company which, through a few acquisitions, is now WSP. I have been with the same company for 19 years. I started out doing building restoration, so that's smaller scale building repair, evaluations of existing buildings, testing and evaluating to find out, why is this building leaking? How can we repair it? And about 4 years or so into my career, I started to focus more on new construction, building enclosure consulting and new construction has been on an upswing in the last 10 to 15 years. It wasn't nearly as common historically. At least in Ontario, it has been common longer in places like Vancouver after they had the leaky condo crisis. But in Ontario, it is hasn't been common as long as it has in other places. So I started focusing on new construction about 4 years into my career or so. And through a combination of learning from others that I work with within my company, external courses, things that I learned working on existing buildings, how buildings fail, I now apply to helping provide advice and input on design of new buildings to help avoid those situations and reduce those risks.
Oh, that's nice. You have a vast of experience of all of this stuff. So thanks for sharing with me.
Yeah, no problem.
Seb, did you tell your story about how you invented your job?
No, I don't think so. I mean, they did talk a lot about random things. Yes.
For people. Yeah.
So I think yesterday when I shared kind of my background and kind of how I got into this field, it was right at the time when modeling was just starting to be a thing, and it was mostly on the kind of compliance side and making sure that you were checking and confirming that you were hitting the minimum targets, which if I were to spin what minimum requirements are, is the worst building you can legally build. So I always had an issue with that, and I always had an issue with just being bare minimum. So I found the need, particularly to, and we talked about it yesterday, to have that ability to translate very complex technical things into actionable items, and through just conversations with architects, realized there was a good niche to do that internally, and to have a lot of these conversations more in an informal kind of collaborative way, and making sure we answer questions at the right time, even if the answer wasn't precise or 100% accurate. But oftentimes we take too long to do very detailed analysis and realize that the opportunity to make change has already passed. So through kind of a little bit of those conversations, I kind of not created, but kind of crafted this kind of in between architects, engineers, computer science, energy models, and have found that there's a lot of people interested in kind of that kind of in between a Venn diagram. So that's kind of how I got to where I am now. And I'm finding, to be honest, the more I am in this field, the less technical work I'm doing. Because software keeps changing. Technologies keep getting more detailed and more complex, and I have a great team that is just smarter than I am. And that's the key, is to find smart people that work with you and that you align with. So now my kind of new role is just to help people grow careers and grow a team and culture around the principles of sustainability and high performance. So I think that's where I am now, and that's kind of that evolving trend of this career. But yeah, and that's kind of how I got to crafting my own title. I guess I should have found a better one, that senior consultant in building performance analysis. That just feels like like a handful.
I'm putting Daniel on the spot. Go ahead.
Excuse me. So sorry. I was wondering because based on my background as a mechanical engineer,
How many kids do you
I
have?
was wondering if I can like do some of because I really passionate, interested in working on energy, building energies. Sorry.
No worries.
For energy building or any kind of like optimization of energy in building or something like that. And I was wondering if how can I go through with this way, because this is my passion and I would like to learn more about this, and that's why I'm here in this workshop in this boot camp. And so do you have any suggestion to start the first step?
Let's see. So you have a good background in, like, your understanding of mechanical systems is already there. So that's a great place to kind of like a good foundation to start. I think what we're seeing more and more is that energy modeling and simulation, it's about understanding all the parts of a building. So my advice would be looking at building sciences, building at the envelope, at the things that Nicole does on a day-to-day, to try to kind of round out that knowledge of how buildings operate. From a technical perspective, there's tools that we use to do models, and some of those are free and offer good support and advice in terms of kind of getting to know how to click the buttons. So a few of the ones that we see in I'd say in the practitioner side, not so much on academia, are IESV, which is software developed in Scotland. The Open Studio, which is a free software that is kind of sponsored or supported by the Department of Energy in the US, or at least until the current administration did what they're doing. And then the third one is Energy Plus, which is, again, another open source one. So my advice on the knowledge side is get more familiar with the rest of how a building operates. On the tools side, download any of these free tools and just click around. Oftentimes, everything I learned by making mistakes, and that's, I think, another key thing is don't be afraid to just try things and make mistakes and learn from them. And the more you make mistakes and the earlier, the more you learn from them. So energy modeling, there's no degree on energy modeling, there's no career, and as a result, you can have any background. It's just how confident you are in just like a self learner and just a curious mind. So those are a few things. The third part would be people and finding groups like this one, like Sustainable Buildings Canada and some of the events that we have, the CAGBC, Passive House, IBIPSA. There's all sorts of communities that kind of are of like-minded people that can give you some just general experience on how they got to where they are.
And I would say that all of that also applies on the commissioning side. A lot of commissioning authorities have their background is M&E consulting and engineering. So having that background also is a great starting point for anyone interested. And I mean, like I said earlier, it can be multiple backgrounds, but M&E background is a very traditional starting point for getting into the commissioning side of things as well.
Farouk, go ahead.
Yes, so I was just going to add what Sebastian was saying regarding the software usage. I agree with what he is saying because from my experience, the first time when because softwares are like a application or a tool. So when a person plays with the tool, they get the hang of it. And the tools are pretty much they're just like billions and millions of commands. So the person can use those tools and then they can know how to generate different projects, different models, different techniques, different ways, different methods. So I'm saying this because I had experience using softwares like AutoCAD, Revit, and I also used IES when I was studying BIM management at George Brown College. And that one was a very interesting software. And you can also generate report using that software that shows, that calculates the energy level of the building. Yeah, that's what I had to say.
100%. And the interesting thing about this field is it evolves with the tools, right? And evolves with techniques. And what it does is it forces you to constantly be thinking about what the software is able to do now and how you do certain things. So it's on that side, it's really geared towards somebody who just is like a lifetime learner, who just enjoys puzzles and kind of continuously updating, which keeps things interesting. Because the way I did things when I was doing my more technical modeling, I have people in our team that say, like, Seba, that's not how we do it. There's a million different ways to do it better, and that's part of being part of a high performance team is kind of acknowledging that the skill sets that one brings, you're not the best at everything, and you just need to collect a group of individuals that are kind of passionate and smarter than you in many ways.
Thank you, Nicole and Sebastian. Thank you so much for taking the time and speaking with our students. Thank you for the great questions. Now we are going to move on to a team activity. So thank you again, Sebastian and Nicole.
Hello, good afternoon, Mudit.
Hello, good afternoon.
Yeah, I was just trying to reach out to you. Oh, hello, everyone. Hope you're ready. We're back from the break. I'm having the pleasure of introducing Mudit Srivastava, Amit, and Jeff. With a passion for developing sustainable building environment, Mudit is a mechanical engineer specialized in designing process optimization to deliver a high-performance building and believe in integrated design approach to see stakeholder expectations by providing them contemporary and cost-effective solutions for achieving projects goal by utilizing low carbon building design strategies along with a deep understanding of thermal system design and sustainable design skill acquired during Masters of Engineering degree. Mudit has gained experience working in several different market sectors. So the stage is all yours, Mudit.
Right, thank you for the introduction. I'll start sharing my screen. Let me know when you can see it. Can you see it now?
There, perfect.
All right. Let me just bring this to the side. All right, good afternoon, everyone. So I'm Mudit Srivastava, and I'll be presenting the high performance mechanical systems that are being designed in today's buildings. And I'll give an overview of what different strategies are available and how can we implement those strategies, which are fundamentally based on the existing technologies that we already have, and then improve the energy reduction targets that are associated with reducing the carbon emissions for the planet. So here's a quick agenda. I'll quickly go over some climate resilient design strategies and talk about like why are we here to begin with. Then we'll explain a little bit about what parametric envelope sensitivity analysis is, get into refrigeration cycles, and I think primarily today I will only be focusing on non-fossil fuel energy equipment. So it will not involve any equipment or any strategies that involves the use of natural gas or any other types of fossil fuels. So we'll be talking a lot about heat pump systems today. So we'll get into air source heat pump system, ground source heat pump systems, and domestic hot water heat pump systems, and then talk about the effects of refrigerants on our climate as well. So let's get into it. I think, like, as you all know, because of the warming climate, because of global warming, the dry bulb temperatures are increasing year over year. And I've just presented some information here for Toronto, and you can see based on this information is from climatedata.ca. They're tracking the climate as it's changing year over year, and what they're projecting is the 2050 to 2080 period will be 12% higher than what we're seeing today. And this is significant when you think in terms of dry bulb temperatures. And, it'll be 17% higher in the last 30 years of century. And given in mind, like, this is an average assumption, there are also different modeled information at different settings. So what you're seeing on the screen here is the blue line, which indicates that if the world is to implement all the strategies that are being recommended, and those are implemented, we will see that the temperatures will not increase that much. And if we allow in our building designs to go business as usual and don't implement, energy saving technologies or carbon reducing technologies in our buildings, it has the potential to go as high as 42C. And this is just medians. So it can, like, you can see, like, if we were to leave things as is and continue using all fossil fuel energy generation sources, we can see as high as 44C of peaks for Toronto. So this is very significant, and I think that's just, I'm just keeping that in mind. We're recommending, this is the ASHRAE chart. I don't know if all of you are familiar with this, but this is what indicates the design conditions for each climate zone. So this is from a weather station. So there are different weather stations located throughout the world, and they collect weather information every single hour for the entire year and throughout the time. So from this we get, like, and this is for the last 20 years. So this is from 2002 to 2019. This is the latest information available for the Toronto zone. And what you will see is typically systems are being designed for this 0.4% condition for cooling. So which is 87.5 Fahrenheit, and this is approximately 28 C. And what we already know, like in based on the recent heat waves that have happened, 28 C is not even close to what our design conditions are. So now what we're seeing more and more is that systems need to be designed for this 97.1 F peak cooling design day temperature, and it's also getting very humid. Like you will see, and this trend is intended to continue, and that's why it's really important for us to be designing systems which do not use fossil fuels and are environmental friendly. So let's get into a little bit of, and even before we get into mechanical systems, and I want to keep this very high level. When there were no mechanical systems available, the only way to condition spaces were to build thick walls. So if you would go to any historical places, where go to forts, you would see how thick their walls used to be. And that was primarily because they relied, in those times, because the technology was not available, they relied on wall thickness to provide conditioning. So, and if you would know, and that was, from those times, that was the way to condition systems indoors, and they used a lot of natural ventilation strategies to condition or to cool their buildings per se. And when it comes to heating, yes, you would have a lot of insulation built in, and that was it. So, and although the good part about that was there was no refrigerants that were impacting the environment to begin with. However, as things progressed, it wasn't the most efficient way of conditioning the interior environment of any building in those times, because it required a lot of material. And as things progressed, refrigeration cycles were developed, and from the development of those refrigeration cycles, we were able to condition the interiors of any building more efficiently with less amount of material. So we moved from more building material to more mechanical material to achieve the same purpose. So, but now it's like, and then the whole industrial revolution happened. A lot of refrigeration cycles were developed, and refrigerants are, from its core, they're not great for the environment. So as we look at buildings today, it's sort of going in reverse direction. What we are trying to do nowadays is to limit the amount of use of refrigerant to begin with, if possible. And if it's not possible, then we try to implement more passive elements. So we invest in more higher performing walls, higher performing windows, utilize low solar heat gain coefficient for windows, so that the solar heat that gets into the buildings and warms up the inside of the buildings, they don't get in, the solar radiation doesn't get inside the buildings to begin with. So as a mechanical engineer, I would, we always recommend to first invest in all the passive elements and then get into the active mechanical systems of the portion. And it's all about this, right? It's all about maintaining thermal comfort for occupants who are occupying these buildings. And you will see, like, the ideal, like in this chart, you would see there's this ideal comfort zone. So this comfort zone, so these are the ranges where we try to maintain the interior temperatures. And there's a very interesting thermal comfort tool. There are a lot of things that play into the thermal comfort. It involves the speed at which air is delivered in the space, if it's being delivered through radiation or if it's being delivered through convection, and what type of clothing people are wearing inside. So there are various different factors that get into the thermal comfort that is optimized for human beings indoors, and this is a chart that optimizes it. So now let's look at the different refrigeration cycles, and you must have learned this in school. This is the typical refrigeration cycle. Basically, you have a compressor, which compressor is where your source of electricity is. From the compressor, it increases the refrigerant to a high pressure vapor, and it goes through a phase change. And from the vapor, there is usually a condenser, and it, when it passes through the condenser, the high pressure vapor again converts into liquid, and with that phase change, you release heat into the environment, or you could release it into different areas, but it results in heating or hot air being distributed. Similarly, then it goes through an expansion device, and then on the flip side, on the evaporator side, what you get is a cooling effect from it. So this is a typical refrigeration cycle that all chillers and all cooling equipment, your refrigerator inside your house, is built on. And the same thing could be, and the only difference when it comes to heat pumps is you just reverse the cooling cycle, and through this reversing valve, and when this reversing valve is introduces, it basically reverses where the heat is flowing. So in your cooling cycle, which is the same as your refrigeration cycle, the indoor coil, the evaporator that you see here, is basically this indoor coil, and it provides the cooling effect. And then this outdoor coil is your condenser coil, which then rejects the heat into the atmosphere and provides a cooling effect to the interiors of the space. Similarly, in a heating cycle, when this reversing valve is activated, the flow of refrigerant reverses, and what happens is it actually instead of drawing heat from the inside and rejecting outdoors, it absorbs it from the outdoors and rejects it inside. So your indoor coil becomes your condenser coil, and then your outdoor coil becomes your evaporator coil. And let's look at what different types of heat pumps are available in the market today, which are really being implemented in high performance buildings. And I've just created like a flow diagram here. So for air source heat pumps, you have different ways you're transferring. So, and actually before I explain that, there is energy generation, and then how you transfer energy once it's generated. So once the energy generation in this sense can be done in two ways. One is through air source heat pumps or ground source heat pumps. And then how it's distributed is you have various different options available in the market. And this is also dependent on the kind of equipment that is available in the market as well. So you can have, from an air source heat pump, you can have a direct air to air heat exchange. You can transfer the heat from air to water, and then you have a water loop throughout your building. And then you have heat exchanger coils, which transfers your heat from a water medium to an air medium. So this would be, your traditional fan coil units that you see in the apartments. And then the third way is you can have an air to refrigerant heat exchange. So your heat is moving from air to a refrigerant, then that refrigerant is distributed throughout the building, and then it then exchanges it one more time from a refrigerant to water. And you'll get more, or like I'll share examples for each of these, and then you'll get a more detailed sense of what these are available. And from a ground source heat pump, so ground source heat pump is basically, instead of utilizing your ambient environment as a heat sink or a heat source, you're instead using ground as your heat sink and heat source. So from this, again, you have 2-3 different options. One is you can have a direct, and with ground source, you always have a water loop that goes into the ground. It could be an open source loop, or it could be a closed source loop. Mostly closed source loops are available in the market today. and they're mostly used in really high performing buildings. But with that water loop, you can either have a direct water to air heat exchange where the heat pumps are located within the space, or you can have a water to water heat exchange, and then you have a water loop throughout your building, very similar to the air to water, and then again have the water to air heat exchange with fan coils. The third way is you can have a water to refrigerant heat exchange, and again, you will have a refrigerant loop running within your building, and then from that refrigerant loop you can either convert that to water or directly to air. So let's look at the first one here. Let's look at the air to air heat exchange. So air to air heat exchange, and you would have seen these in small apartment buildings. These are basically small air to air heat pump systems, and which are split. So in this one, this outdoor unit that you see here, this is your evaporator or condenser depending on the season. It has the, and to go back to this diagram here, the outdoor unit contains the outdoor coil, the expansion device, and then the compressor in it. So this unit, it has the three components built in, and what you have on the indoors is just the evaporator or the condenser coil depending on the season. So this just has the heat exchange coils. And again, like these are very commonly used in smaller scale projects. You can have one outdoor unit connected to one indoor unit. You can have one outdoor unit connected to two or multiple indoor units. And again, the good part about these is these are now designed for cold climate application as well. So you can have heating all the way down to minus 25F, and even in some instances even lower. So you can meet the full heating demands of an interior building with this type of equipment. You don't have to rely on anything else. They run on electricity, as I mentioned earlier, as you would know for all heat pumps. So yeah, there are some, there's some more information. The good part about this is this is also based on inverter technology, so it maintains the efficiency very nicely. And then again, like these are some of the performance data that you can have. So one thing I do want to note is like the main advantage of utilizing heat pumps is the COP, which is the coefficient of performance, which essentially means that if your input electricity is 1 kilowatts, you can get 4.5 kilowatts out of these heat pumps. So your energy input is low, and you're able to generate more heat from the process of refrigeration and the heat pump cycle. And this is primarily one of the reasons why heat pumps are so good for the environment, and they're the equipment that will be implemented from now and even for all the future projects, because they don't rely on any natural gas. So just as a comparison, any fossil fuel generating equipment, it has an efficiency of less than 1. If it's electric, it's a COP of 1, which means you have 1 kilowatt input and your output is 1 kilowatt as well. But with heat pumps, your input is lower and you get much more out of those. So that is one of the major ways how we are reducing the energy consumption, not just for individual buildings, but for at a larger scale grids as well. Another type of heat pump that is now available in the market, which is, it makes it even more compact. So in this previous system type, you had one outdoor unit and one indoor unit. In these type of units, now all of the components of the refrigeration cycle are within one unit. So you have your outdoor coil, you have your indoor coil, you have the expansion device, and then your compressor all built into one unit. So the advantages of these units are it can be applied on like very, very small, like individual rooms. These are usually seen in hotel suites quite a bit, and even like small studio apartments have some of these. I don't want to get involved costing too much into this discussion, but like these are traditionally also very cost effective. So from a construction perspective and a capital cost perspective, these are also very low, and they have its application. Although these are not applicable for large rooms like auditoriums or things like that. These are very involved in small scale systems. Again, these are just different options for it. They work on really low GWP refrigerants, which is great. The other good thing about these is the amount of refrigerant charge is also very low. So as I mentioned earlier, refrigerants also they have a direct impact on climate change, and with these type of systems, the amount of refrigerant that you need is pretty low as well. Again, yeah, these are just different types of installation. They can be installed low overhead installation on the side. It just needs to be on a wall, which is an exterior wall, because they take the outdoor air and the air heat exchange with the outdoor environment happens at this wall. So they just need to be on an exterior wall. And these are just some capacity information that I've put in here for reference. Let's look at a different type of heat pump, which also involves an energy recovery ventilator in it. So this equipment is taking it one step further. Not only is it providing conditioning, but it is also providing ventilation air for the indoor spaces, and it performs these 7 functions in a single unit. And it's a very, very neat product of engineering, where it can perform heating, cooling, ventilation, air purification, dehumidification, free cooling, and even heat recovery, depending on what the outdoor air temperatures are. So again, similar to the previous product, this also has all the components of the refrigeration cycle within one box, and it has its applications. These are the constraining factor with these is it does not have high capacity options. So these are only available in a maximum of 1 ton units. So this is appropriate again for small rooms, small suites. If you have if it's an office building and there's like one office, small office, it's appropriate for that. But again, every product has its applications, and I'll as we go through different types of high performance systems, I'll try to explain where these are usually applied. And again, like here's some more information. Like it has a really high efficiency ERV core built in. As you can see, like it has 86.7% sensible effectiveness, which is really high. And this is one of the primary ways of reducing energy consumption with your ventilation air, which is required for proper indoor air quality in all buildings. There's just some diagrams of how it operates. It is ceiling mounted usually. There's also vertical configuration that is available. You'll see they're also don't occupy too much space, but it functions very well for such small spaces. Some cooling performance data. They operate down to -20 C. They output about 1.75 kilowatts, and at 35 C, they output about 2.4 kilowatts of cooling. They do require a little bit of preheating because to protect this ERV core, this ERV core needs to be protected. So when the outdoor air temperature drops below 15 F, you have an electric preheater which protects the core. So it preheats the air to -15 F, and which then enters the energy recovery ventilator. Okay, so let's talk about, so these were all equipment that were directly transferring from air to air. So this, we were looking at an air to air heat transfer approach with heat pumps. Let's look at air to water heat pumps. So basically what happens in the air to water heat pumps approach, like your outdoor coil remains the same, which is open to the ambient environment. Your compressor and the expansion valves remain the same. The only thing that is different in an air to air, in an air to water heat pump is on your heat exchange coil. It's a refrigerant to water heat exchange coil instead of a refrigerant to air heat exchange coil. And what this does is it allows you to have a chilled water and a hot water loop throughout your building, which you can then utilize to heat or cool spaces. And I'll get a little bit into it. How is the effectiveness of each what do you call it, like air or refrigerant or water? Like, what is the most effective heat exchange variant? So from when you compare these three, refrigerants are most effective at transferring heat because their heat capacity is the highest. Then comes water, and then the least efficient way of transferring heat is air. So what we want to do is rely on a combination of those two, so that when you're only doing it with refrigeration, you're also including a very high amounts of refrigeration and refrigerants in it. So to design really high performance systems which are a balance between water heat exchange and a refrigerant heat exchange is the strategy that is being used in the industry nowadays to optimize both heat exchange versus the amount of refrigerant that you have in systems. So in this one, you have this heat pump. You can either generate hot water or cold water through it. You can store it in storage tanks. You typically, with these type of systems, you have small pumps which circulate the water throughout your building, and then you have some fan coils or just radiator coils, which then become your terminal heat equipment of how you transfer heat to this actual space itself. Again, like it has operating temperatures, which are, for the longest time, like the air source heat pumps were only available where you needed an auxiliary boiler with it. Because if your temperatures are below 7F, what happens is the refrigeration cycles gets into defrost mode, and it becomes really difficult for it to operate, and it turns off because of high pressure conditions. So in order to balance that, what typically is done with these air to water heat pumps, you have an auxiliary heating source. So when your outdoor air temperature drops below 7F, this auxiliary heating source is what takes care of the heating and for the heating of the building. And again, this auxiliary source can be an electric boiler, or it could be a gas boiler as well. Because the number of hours in an year are so less when you are less than 7F, it is a strategy that is being used to utilize gas boiler just for those few hours. Because when we go with electrical boilers, what happens is your electrical load for your entire building becomes extremely big, and this condition becomes even more worse with the scale of your project. If it's a really big project, then it's really difficult to have an electric only boiler, because the costs associated with your increased electrical capacity will be huge, and it will be a huge impact on the local grid as well. So again, like it's a balance that you have to maintain, and it depends on from project to project. Again, like in these heat pumps, it can create either chilled water or hot water, or there is a mode where it can even create simultaneous chilled water. Usually this is how the distribution loop looks like. You have a loop throughout your building with your auxiliary heater, and that would maintain your loop temperature throughout the life cycle of the project. This is just this, it's just the same heating and cooling modes of operation for the heat pumps. And then there is another way where you can actually combine the heating and cooling loops, where instead of when you have a cooling load, instead of rejecting heat into the atmosphere, you can actually reject it into your heating loop. What that does is it reduces the energy, the electrical energy you need to run the compressors within the heat pumps. So this is a 4-pipe distribution that is implemented in some projects. Now let's look at a different type of air source heat pump, which is an air to water heat pump. But the difference in this is it is a packaged unit which can simultaneously produce chilled water and hot water. So in this system, these air source heat pumps, they were either producing cold water or hot water. They could not produce both at the same time. However, in these type of package systems, these are the latest technologies that are available in the market now. What they have done is they have combined different modules back to each other, and one module can create chilled water, whereas the other module can create hot water at the same time. And you're just extracting your heat, so your cold water loop. So what's happening is your building loop is running, your water coming from your building is at 54F. It goes into this module, the refrigeration cycle works, and the water comes back at 44F. So the water gets cooled. At the same time, the heat is rejected either into the atmosphere or it could go into the hot water loop. So this technology utilizes the heat that is rejected from the cooling loop. It is actually absorbed by the heating loop. So when it is operating in this simultaneous mode, the electrical consumption is way less because you're not running compressors to produce your hot water or chilled water. When it's operating in a single mode, each compressor is run and it creates a chilled water loop. And again, these type of systems are extremely beneficial when you have buildings which have very deep floor plates. So by that, what I mean is when you have a building which has, so in buildings, you typically have an exterior zone of about 12 to 15 feet. And then if your floor plate is bigger than, let's say it's 90 feet in one side, and it's a rectangular 90 feet by 40 feet. And in the middle space, because your exterior loads are being dealt with, your interior spaces are always cooling only spaces. They would always call for cooling because your exterior zones are already maintained at the space set point temperature. So your interior zones all only have cooling loads. So these types of systems are used in those buildings which have simultaneous loads at the same time, whereas your exterior envelope or the exterior zone can be running in heating mode, but the interior spaces which have no outdoor exposure will still be running in cooling mode. And this is where it's best applied. These are also very, dimensionally wise, these are pretty compact units. They're typically installed on the roofs, or if you have floor space available on the ground, these can be installed at grade as well. But typically these are installed on the roof. Again, here's these also operate, and I think the one thing about these type of heat pumps is that they can also operate on low ambient temperatures. So remember earlier I mentioned that you need an auxiliary boiler source because the heat pumps could not operate less than -7F. However, with this new technology that is now available, and this has come out in like last 6 months. So with this, mechanical evolution, we are now able to eliminate that boiler source that you would need in your buildings to heat it at even minus 25F. This is just some performance data, like at 95F, you can see it has an EER. So EER is another measure of cooling efficiency. When you convert that to a coefficient of performance, you just divide it by 3.413. So again, like basically what that means is with 1 kilowatt of energy that you input, you will get around like 3.4 out of it. Similarly, in the heating system, you can see even at minus 5F, if you're inputting 1 kilowatt of energy, or let's say 100 MBH of energy, you'll get 209 out of it. So it's twice as efficient even at minus 5F, but as the ambient temperature increases, it becomes more and more efficient. So when you're at about 2 degrees Celsius, 3 degrees Celsius, you're getting 3 times the heat out of your heat pump, whereas your input is only 1 kilowatt. And this is what makes these heat pumps so efficient and good for the environment. Okay, so that was our air to water heat exchange. Let's look at air to refrigerant heat exchange. And as I mentioned earlier, like it takes the most amount of energy to transfer energy through air. So, and when you transfer it with refrigerant, you can transfer a lot more with very less space consumption. So if you were to, let's say, if you were to transfer the same amount of energy from one place to another, it would take an 18-inch duct. Whereas if you were to transfer it through a refrigerant, you would only require a 1/4 inch of tube of refrigerant. So again, like when we look into our construction industry, this becomes really important when you factor this in with the architectural design, with the structural design. So it requires much less amount of space for your mechanical distribution. However, again, you have to balance that with how much refrigerant you have in your overall project, because then reducing the amount of refrigerant is overall good for the environment. So this is just a balance that you need to make. But from these air to refrigerant heat exchange units, these are the units that typically go on the rooftop or on your exterior grade. It transfers the energy from air to refrigerant, and that refrigerant is then run throughout your building to your fan coil units, where your fan coil units have a refrigerant to air heat exchanger. So first it transfers the energy from air to refrigerant, and then from refrigerant to air directly. So this is that option where that source is utilized. And again, you have refrigerant pipes that run throughout your building. You have these branch selector boxes, and then and the good part about this type of system is it can provide heating and cooling simultaneously. So if one zone is calling for heating and the another zone is calling for cooling, it can operate like that, because these branch selector boxes are the point of disconnection from the main unit. And what it can do is, like, it can transfer, again, it's the same concept, it just happens in the refrigerant form, is that the energy that is rejected from the refrigerant, it is absorbed by this branch selector box, and it can provide heating through that. However, we have a hybrid VRF option also available now. And again, this is primarily to do with reducing the amount of refrigerants that you have in your building to achieve your conditioning needs. As you can see in this one, the only difference is all these pipes that you see here, all of them have refrigerant. And what that does is it increases the amount of refrigerant significantly in your building. So another strategy that engineers have come up with is to limit the amount of refrigerant only between this outdoor unit and this branch selector box. And what happens inside this branch collector box is you have a refrigerant to water heat exchanger. So then you have small pumps inside this branch collector box, which runs water to your indoor coils, where it can exchange heat with water. So in this instance, what's happening is your energy is being transferred from air to refrigerant. It then converts from refrigerant to water, and then ultimately from water to air. So it changes phases quite a bit, but when you look at it wholesome from a building level perspective, it reduces your amount of refrigerant significantly. This is just how a typical layout looks like in buildings. It can be implemented in residential buildings, office buildings, institutions, anywhere. The application for these type of systems are quite many. The last air source heat pump equipment I want to go over is the refrigerant to water heat exchange directly. So it's the same concept as this hybrid VRF. All it's doing is, instead of going to a branch selector box, what happens is the heat is being transferred from air to refrigerant, and then refrigerant to water. And that at your building level, you can have the same hydronic loops to provide heating and cooling for your building. So what this does is, in this type of arrangement, you can have, let's say it's a 20-story building. You can have these equipment sitting outside, and then you can have long lengths of refrigerant piping that are running throughout your building. What this system does, it reduces the refrigerant load even less. So now the only refrigerant that you have is between your outdoor units and your refrigerant to water heat exchanger. And these are usually very close to each other. These are located on your rooftops, in the mechanical penthouse of buildings, or, it could be, they're very close to each other so that you can limit the amount of refrigerant that you have in your system. And then you get the benefits of your hot water and chilled water system throughout your building as well. Again, these are the types of components and units that are available in the market. They're very compact. They can be installed easily on the rooftops. And then these are the refrigerant to water heat exchanger modules. And the good part about these is these are modular. So as let's say, for whatever reason, in 20 years from now, the environment became too hot and you needed to add more cooling capacity to it, you can add a new module to this and you could increase your building's capabilities. So I think one other thing that is happening in the industry in high performance building designs nowadays is that you're going with these modular approach, which provides more flexibility for the building owners to increase capacity in the future. And the limiting conditions for these are like it creates hot water only up to 115F. However, like in most building applications for space conditioning, you don't need hot water which is hotter than 115F. Similarly, it operates down to -22F, and it can produce 45F chilled water for your loop. And again, for whatever reason, if there was a need, if there was a process load, by process load, what I mean is if you required hotter or more chilled water than these values mentioned here, you can have a subsequent heat pump system. So it's a refrigeration cycle stacked on top of a refrigeration cycle. So you can have, it's a cascading refrigeration cycle, which can provide temperatures as high as 150F and even like as low as 20F if there was a need for it. Usually it's not required, but for universities and like large scale buildings where you have different space usage types, these are utilized. And in all these generation equipments, these are the type of terminal units that you have. So in this, the terminal unit, basically you have a hot water and chilled water loop running throughout your building from your air source heat pump. And this is how you exchange heat within your space. So it could be a classroom, it could be a residential suite, it could be an office. So you can have like these type of fan coil units, which exchanges heat from water and it introduces heat or cold through air directly in your interior space. These are just some dimensional information. Again, I'll skip through these. The other types of units are these horizontal types of units. And again, it can be either 4-pipe units or 2-pipe units, and they perform the same function. Your heat pumps are at the central level, and then at the terminal levels, you have these fan coil units which deliver the heating and cooling directly to the space. And again, these terminal units, and let me go back, like these terminal units do incorporate a fan in them, so there is an energy associated with these types of units. However, there is an even better way of transferring heat from water, is to do it through radiation. So what happens is, with these type of systems, you have radiant ceiling panels, or you can either have radiant floors as well. So instead of blowing air and having a fan to blow air throughout your space, this type of terminal unit, what it does, it runs the water throughout your space, and through radiation it provides comfort within the space. The good part about this type of system is that it's the best form of thermal comfort that you will ever achieve, because with any type of forced air system, what happens is, wherever the fan coil unit is located, or wherever the duct outlets are, your supply outlets, you will have more comfort there, but you have the possibility of creating like hot spots or cold spots in certain spaces which are not uniformly distributed. However, when you have the radiant systems, the thermal comfort is very superior, because you have very even temperature distribution throughout your space. And because there is no fan, it reduces the least amount of energy. You get a lot more of ceiling space, because you don't have any ductwork installed with this. And because there is no fan, there is no noise that is generated from this, so there is no noise issues as well. And this is primarily, there's no moving mechanical part in this, so there's no mechanical maintenance requirements for these as well. So from a long-term perspective, from an operations perspective, these are also fantastic. A similar approach is with chill beams. These are just terminal devices. You go through the same hot water chilled water loop, and then you can distribute your heating and cooling through the space. Again, this also doesn't have any fan, but it induces the air and provides the heating and cooling needs. Okay.
Mudit, I don't want to
Yep.
stop your flow. I know you've got tons to go, and this is the most important one right here.
Yes.
But there are a ton of questions, and unfortunately, our team is unable to ask them. So just want to make sure you leave a tiny bit of time at least to answer some of the questions at the end.
Yes,
But
will do. I'll try to go a bit quicker. Yeah. All right. Let's look at, so that was all the different types of air source heat pumps that are being used in the industry for high performance buildings. Let's look at ground source heat pumps. So for ground source heat pumps, I think and let me give a big overview first. So basically you have different temperatures and different types of basins. So in the western part of Canada, you'll see there's a lot of hot sedimentary basins, there's hot volcanic basins as well, and then you have direct heat exchange systems in most of southern Ontario, a little bit in Quebec, and all towards the eastern Canada as well. So, and at a higher level, these high temperature electrical generation, so wherever you have these high temperatures, you can actually run power plants from it, so you can produce energy at a really large scale. However, in where these direct heat exchange systems are available, you can run heating and cooling for your building. So that's what are called direct heat exchange systems, where you can have geothermal loops under your building, outside of your building, and then you can extract heat from the ground and reject heat into the ground instead of air. And again, something else with these type of systems is that you have different ground temperature. So as you go deeper in the ground, the temperature becomes warmer and warmer, and the impact of your ambient air reduces significantly. So with any ground source heat pump system, the deeper you go, you will get more stabilized temperatures with the ground. And what that does is it increases your ability to reject and absorb more heat within a compact area. Like if we were to go with, less deeper boreholes, you would need a much larger area on your site to get the same amount of heat exchange. So again, there are also some constraints that are associated with geothermal systems. You have bedrock available. So this is one of the constraints that are, so in the Kingston area, in the Ottawa area, there's very hard bedrock. So it's really hard to drill deeper in those areas. And that is a constraint with geothermal in those specific instances. But like Southwestern Ontario and the GT area is actually perfect for it, and that's why you're seeing a lot of geothermal projects go into the spaces now. Another constraints are there are some open wellhead protection areas, so you're not allowed to drill in those areas because people use drinking water from them. So these are the constraints. Quickly skip over, the advantages of these type of systems are, you don't require any rooftop equipment. You can improve your structural design. You can utilize less structural elements to support your building because you don't have many higher mechanical equipment. You don't need any, as you saw with some air source heat pump, you required a gas boiler or like an electric boiler backup. With these type of systems, you do not require any sort of gas backup. And then again, if your space is free on the roof, you can utilize that to install solar PV panels, which are again some of the other renewable energy techniques that are available. So a typical geothermal field would have like boreholes like this. You would, and this is just piping. It's a high density polyethylene piping. It's installed deep in the ground. It's filled with grout, and then once it's grouted, like you fill it with the fill material, and then you get the heat exchange from this. Again, I think actually the annual geothermal balance of the field is also important, and I don't want to get too much into it. Let's look at the different types of water source heat pumps that are now available now. So in this type of heat pump, it's very similar to air source heat pumps. The only difference is, like in this, your outdoor coil, instead of rejecting and absorbing heat from the air, it rejects and absorbs heat from the water. That's the only difference. Again, it comes with your source and sink heat exchanger. Instead of it being a air to water heat exchanger, it becomes a water to water heat exchanger. Again, these are also available in simultaneous mode. They're available in individual heating and cooling modes. And this where you see on the green here, the source and sink water. So this is what goes to the ground. So you have this as your source and sink water. And then on your building side, you get chilled water and hot water. And all your refrigeration cycle is happening inside these units. So these are your compressors. Then you have an expansion valve. Everything is built into this unit. It's just that your heat exchange coils are different. So that is one system where you have a central plant. You can have a central plant and then you can distribute water throughout your building. The other option is to have the heat pump built within the space. So you have your groundwater loop that runs throughout your building, and you can have the compressor, the expansion valve, and the heat exchange coils all within the suite itself. So it's a similar style of unit. These are very frequently used in apartment buildings. They're also sometimes used in office buildings as well to provide heating and cooling. So the heat pumps are built into this, and then you have a central circulation loop throughout your building which runs your groundwater. And these are some different types of horizontal heat pumps which are installed in ceilings. So again, like very similar to vertical style units, these are now installed in ceiling, but the concept remains the same. You have geothermal water running throughout your building, and then you have the compressor, the expansion valve, and the heat exchange coil in it. Okay, let's look at domestic hot water heat pump systems. These are again primarily air sourced type heat pump systems, but these are just utilized to to increase the temperature of your hot water, domestic hot water. So your incoming temperature, your incoming water that comes in at 40 degree F, it lifts it to create 150 F water, and you can store it at the storage temperature in the storage tanks at the 140 F storage temperature. But the concept again remains the same. These type of heat pumps are air to water heat pumps, and then water is stored in the storage tanks before distribution. Another way is similar, like, these are for larger air source heat pump system. Is just the difference is just in capacity. The concept still remains the same. And the best part about these is they use CO2 as a refrigerant, which is the best kind of refrigerant that you can use. So again, I think as people are designing more and more systems and new type of technologies are becoming available, utilizing CO2 as a refrigerant is the way to go, because it's really the best kind of a refrigerant. It has a global warming potential of 1, which is what every other refrigerant is being compared to. Wastewater heat recovery. These are other type of heat recovery systems. So basically what this type of systems do is they utilize the wastewater from your buildings. It stores the wastewater in a wastewater storage handling tank, and then it uses the heat that is available in that wastewater, and it utilizes a refrigeration cycle. So it utilizes a water to water refrigeration cycle. So you have water on this side. I mean, it's mixed fluid, like solid handling pump, which moves the water through it. And then on the other side, you can get low degree heat, which you can use to preheat your domestic hot water. So because your source is free, you can utilize that, and if this were not being used, this would just go out into the city system, and then it would not have extracted energy out of it. But by utilizing a little bit of electric energy, you can get some heat output from it. So these are also very frequently used nowadays in high performance buildings. And lastly, I just want to wrap up with refrigerants. I think refrigerants, as I mentioned earlier, they are one of the most significant sources of environmental degradation. And I think as we move towards 2026 and then towards 2040, we intend to use low GWP refrigerants, which are not as bad for the environment. And, I just wanted to present here that, refrigerants, because when they leak, you don't see them. So we don't really understand the impact of refrigerants that they have on the environment. So if 100 pounds of R410A, and R410A is the most common refrigerant that is used in the HVAC industry, if it's 100 pounds of that is released, it is equal to 10,600 gallons of gasoline consumed. So it's huge, and which is why I keep stressing on utilizing less amount of refrigerants as possible, and then if not possible, then utilize low GWP refrigerants. There are many options that are available in the market today, so I've just put it here for reference. That's all I would like to conclude here. Like these, again, like I would, as a mechanical engineer, I would highly recommend that high performance systems are being used. But yeah, that's it. I'm open to questions if there are any.
Go ahead, Dia.
Hello. Well, thank you for all the information. It's very useful. I have a question regarding the COP of heat pumps. So if we consider water source heat pump that produce in 3 scenarios. First scenario produces chilled water for cooling, space cooling. Second scenario, it produces hot water for space heating. And finally, it produces like very hot water for domestic hot water use. So how the COP would vary between the 3 scenarios? Which case would be the higher and which case would be the lower COP?
So with heat pumps, so whenever you're trying to transfer heat, the domestic hot water, so the more hotter water you generate, the less efficient it gets. So let's say if you want to generate 180 F water, your efficiency of your heat pump will be the lowest, and that has to do with the lift. So the more the lift, so let's say you have your condenser water loop or your ground loop. Your ground loops typically operate around, depending on your project, they typically operate around 40F to 40F entering to your leaving water at 32F or 33F. So now essentially, and at the thermodynamic level, what you're doing is you're transferring it from 30F to 180F. So the higher you go, the higher your lift is, the lower your COP is. And which is why in one of the slides I mentioned that for space heating needs, the reason why we only heat the water to 105F is to improve the COP of the heat pump.
Yep.
Yeah, so that's I hope that answers the question. So it's the lower the lift, the better your COP will be.
Yeah, I see.
Yep.
Thank you so much. Yeah.
Mudit, I don't know if you can see the questions in the chat, but if not, I can read them out to you.
Let me go back. Okay. Okay, I see we have a question about air leakage through wall heat pumps around the units. Yes. So yes, I agree. There is significant, like it's from when you compare that system from an overall product perspective, there are instances which, due to the construction methodologies, there is air leakage. Again, that is why it's not the best system to use. However, it is an air source heat pump system. It is any day still better than a gas-fired boiler or any other equipment. But yes, when you're comparing different heat pumps at the same time, the ones that are at the walls, they do have some leakage associated with them. However, with your construction managers, this is also something that can be managed on site, on how well the detailing is for that construction methodology. Like how is it sealed, how when they're creating the holes for the outdoor air and exhaust air in discharges, like how is that detail, how is that architectural detail around those openings. So it can be mitigated, but yes, overall there is some air leakage associated with it. And then I think because usually it was used. Yeah, so I think the second question from Sophia is it talks about how air rises within a suite. So again, like if it depending on, so your discharge and so the other thing that I didn't cover here is displacement ventilation. So whenever you're discharging air, it is always best to discharge it at a lower height, because in your from an effectiveness perspective, in your heating mode, you're also dispersing the heat at a lower level, and it also carries. So when you have people in the environment, like humans are actually the worst actors in terms of indoor air quality. Like there is nothing else inside a room which is more harmful than humans breathing in terms of bacteria and everything else. So when you have air discharge at a lower level, what happens is like it takes all the bacteria in a single pass. So you keep your return air grills up high and your discharges at a lower point. So from an indoor air quality and distribution perspective, that is effective. However, as long as the efficiency of the heat pump goes, like there is no difference in it. Like there's no difference in, it's just a location of where you're discharging the air. Like in terms of the effectiveness of the heat pump, in order to generate energy, like there's no difference. As long as the heat pump is within the operating envelope of the local conditions, of the ambient conditions, it'll be the same. What else? On air to water systems, how do you manage the condensation in the conditioned space? Yes, so when you have these air to water systems, when you have water being distributed throughout your loop, you do have like it's basically you're only doing sensible cooling. So your condensation or the latent loads for your space are usually handled at the ventilation system level. So it's usually done at your dedicated outdoor air supply unit if you have those. And if you don't have those, if it's just a typical if it's just a split system, then you do need to provide dehumidified air to your space. So it happens through your ventilation air system. And I think this is another thing that we should keep in mind, is that space conditioning and ventilation air conditioning are two different things. In some systems, they are combined together. In larger systems, they are usually separate. And from really high performing buildings, it's beneficial to keep them separate, because you don't want to handle the latent loads by your terminal equipment, because it, first of all, it would create condensation, because whenever you have condensation, then in your fan coil units, you need to provide a drip tray, because condensation will take place. And then from that drip tray, you will connect it to your condensate system throughout your building, which is again, like it's a capital cost expense. So these are some other factors that you have to factor in as well. But for really high performing projects, it's best to keep them separate. So handling your latent loads at the central air handling unit level is the approach that is being implemented in really high performing projects. I think there's another question from Sophia. She mentioned why a building would have to heat and cool the building at the same time. I know most condos, for example. Oh yes, so yes, condos. So condos, it's very different. So this, like when you have heating and cooling needs at the same time, what I meant is you can have a big retail space, like even in multifamily residential buildings, you can have a huge retail space at the lower floors of your building. And because you have, and maybe it's best explained. Maybe, Bettina, I'll share my screen quickly. So what I meant by interior spaces, so when you have a building like this,
we're not seeing your screen yet. Oh,
can you
there
see
it comes.
Can you
There
see
it
it now?
comes. Yeah.
Yeah. Okay. So when you have big, deeper floor plates in your building, what you do get is you have this exterior zone, which is about 12, I want to say 12 feet to 15 feet in depth. So you have different equipment for this exterior zone. So now when you have this exterior zone that is satisfied at the temperature that you have specified. So let's say this exterior zone is maintained at 75 F in cooling and then 70 F in heating. Anything that is in this interior zone, basically it is not exposed to the ambient environment. So what's happening in this interior zone is all you have is heat losses from interior lighting. You have heat losses from your equipment in the space. You have heat losses from humans in the space. So basically there is a lot of heat that is rejected. So you need to cool that heat to maintain the space set point temperature. So that is why I was saying is that there can be instances where you have and this specifically happens when you have like deeper floor plates or you have different types of space usage within a same building. So you can have your exterior zone in a heating mode, whereas your interior zone can still be calling for cooling. And this is where those types of simultaneous systems are best utilized. I hope that clarifies the question a little bit. Yeah. And then I think, does it have the same efficiency in each part? Yes. When they're operating in the simultaneous mode, the COP is exactly the same. So the COP is higher. So the COP is, let's say, if it's working in your heating mode, if your COP is 3, and if it's working in your cooling mode, if your COP was, let's say, 2.5, but when it operates in simultaneous mode, the COP is around 5, around 6. It can sometimes you have heat pumps where it's even as high as 7. So what happens and the primary reasoning for that is you're utilizing your compressor less in that time. So your compressor uses less. So the amount of electrical energy, the amperes that are actually being utilized by the equipment are much less in that time when it's operating in simultaneous mode. So your input energy is much less, but you're still getting more out of it. So in this case, basically you're getting the same output, but your input has reduced because it's working in simultaneous mode. And that's why the COP is simultaneous, and it's the same between heating and cooling mode. So the simultaneous to adjust and maintain an optimum temperature. No, it's just so the question from Syed, I think. So the simultaneous mode is only utilized in like larger buildings where you do have simultaneous heating and cooling needs. When you can still maintain temperature without using simultaneous mode. It's a way of utilizing the heat rejected into the atmosphere instead of utilizing it to heat a little bit of it. So you're in a way, yes, you're maintaining the loop temperatures by it, but space temperature, no. Like you can maintain space temperature without simultaneous operation, but you would need like different equipment for it. So if a simultaneous machine was not available and you had you have a cooling need and a heating need at the same time, you would have different heat pumps for them. You cannot have the same heat pump. So the advantage of simultaneous heat pump is that you can have one equipment and still generate both. So you're reducing on your capital cost expense for your mechanical equipment, and you're also increasing the efficiency of the overall system. What else? There's a question from Danielle. Can heat pump systems include outdoor air mixers to meet necessary ventilation rates? Yes, they can. So basically these are typically done for projects where, let's say it's a warehouse project. So in warehouse projects, what happens is you have rooftop units, and the rooftop units have built-in air source heat pumps that are outdoor. But in those types of applications, what happens is it's not an 100% outdoor air system. You recirculate the air a little bit throughout your space. So when that recirculation is happening, what happens is you're mixing your return air with your outdoor air, and you get a mixed air temperature, which the heat pump then utilizes to provide the heating and cooling for that space. So yes, you can use that, but what the disadvantage of doing that is that you need a lot of airflow and to transfer the same amount of energy. And when you need more amount of airflow, what that means is you need much more bigger ducts. You need a lot more, your fan energy increases because the more airflow you need. And as you know, based on the fan laws, CFM is directly or not directly, it's like it's proportional to the power of 3 for power, right? So the other way of saving energy is to reduce the amount of airflow that you're moving within your buildings. So that's why it's like in really high performance systems, you would see that they are not recirculation type of systems. And the primary reasoning for that is that you're reducing your fan power consumption by only distributing outdoor air and not recirculated air throughout your buildings. But maintenance. Maintenance of refrigeration units, it's like, once or twice in a year. And then in terms of lifespan, most air source heat pumps are between, the smaller ones tend to last a lot longer. They're mostly between 15 to 20 years for the heat pumps. So that's a typical lifespan for these air source heat pumps. And that's a good point, right? That I think like it's relevant to our conversation is that the reason why ground source heat pumps are so popular, because you don't have to replace, once you install a geothermal borehole field, it's good for 100 years. So you don't have replacement costs that are associated with ground source heat pump loops that you do see with air source heat pumps, because like that, your ground is acting as your plant and you're just running water throughout it. However, on the interior of the building where you have the interior heat pumps, they do need to get replaced and they have like similar lifespans. But from an overall plant level, that is one of the advantages of having a ground loop system, is that you don't have replacement costs with it. There's another question from Sophia. Can this technology be used to heat and cool water for the building to like sensor? Yes, yeah. So the domestic water heat pump systems that I showed earlier, like those are the technologies that would be used to create domestic hot water systems.
Terrific.
Yeah.
Mudit, my apologies, but that is the end of our speaking time and our questions. Thank you. Thank you so much for staying on and answering all these questions. We're going to invite you to our LinkedIn group so that the students can continue the conversation.
Right.
Great. Thank you all for so many wonderful questions and insights from Mudit. I think that was really fantastic and successful session. I have the pleasure of introducing Shoshanna to you all, who is going to be talking about a very exciting topic today, which is, I believe, embodied carbon and life cycle assessments. Shoshanna is an associate professor at the University of Toronto's Department of Civil and Mining Engineering, and I think you are going to get a lot out of this session. So welcome, Shoshanna.
Please let me know if anything doesn't work. Also, I can't see most of you, so if you want to ask a question, please actively raise your hand or unmute yourself and ask it. So very nice to be here. Thank you for having me. I'm going to talk about what future we should build, in particular in regards to resource use and embodied carbon. Have you already as a group been through embodied carbon, or should I explain what it is as I go, the basics?
I think a quick review of the basics of what embodied carbons is wouldn't go amiss. Thank you, Shoshanna.
Okay, great. Thank you. So my talk is at the interface of these two challenges. We have two very 21st century things going on. On one hand, we have the massive infrastructure deficit, the housing crisis, this desperate need to move fast, build things. We need more staff, more housing, more public transportation, more bridges, more repair, more parks, more seating, right? Just more all the time. And on the other hand, we have the climate crisis and other challenges of ecosystem collapse, which demands we do less. We extract less from the earth, we use less, we pollute less, we tread lighter on the earth. So how do we do these two things at once? How do we simultaneously do more, and less? And that's a really hard challenge. That's what we'll be talking about today. And also, how do we do this in a relevant timeline? Right? These are not problems we want to leave festering for another 150 years. I mean, ideally, we don't even want to leave them festering for another 3 years. So we have these big challenges and short timelines, and that's three wicked problems all squished together. There are many ways in which we could talk about this. We could talk about energy, we could talk about building operations. I'm going to be specifically talking about resource use and embodied carbon. And why is that important? As we have gotten better at making clean energy, as we have gotten better at designing energy efficient buildings, we have used more and more materials, both per person and overall. And the share of GHG emissions and other pollution coming from materials has gone up. So in 1995, the GHG emissions coming from resource extraction was 15% of total. By 2015, it was 23%. We now think it's around 40%. So all of the GHG emissions in the world are somewhere around 40% due to getting materials out of the ground, processing them, and turning them in to things that we can use to build. And of course, we don't only use plastics and rubber or iron and steel to make buildings and infrastructure, but that's the lion's share. We use most, especially concrete, about half of iron and steel is really heading towards buildings. So if we're talking about embodied carbon, what does that mean? So generally that means the GHG emissions, the greenhouse gas emissions associated with getting the raw materials out of the ground, processing them into something we can use. So going from iron ore to steel I-beam and putting that into the building. Some people also then include in embodied carbon any extra materials we have to add in during the building's lifetime and the impacts from end of life. But generally, mostly what we mean is cradle to gate. So we got the limestone out of the ground, we heated it up to turn it into clinker, eventually it was made into cement, we mixed that with other things to turn it into concrete. All of that takes both energy and releases emissions from the chemical reactions that go in as you form the product. So as you turn iron into steel, greenhouse gas emissions are released to the environment, even if you use perfectly clean energy. It's about 50-50 between energy and these chemical reaction called process emissions. Same thing with concrete. As you're going from limestone to cement, you have a chemical reaction which releases GHG. And so even if we have perfectly clean energy, that's still going to happen, which means that these sectors are very, very hard to decarbonize. Even if we get to perfectly clean, magic, no emissions associated with energy, manufacturing these will still have emissions. They'll be about half what they are now, but there's a big difference between half and zero. So this leads to the question we're talking about today, which is given the challenges, we want more, we need to pollute less, the challenges associated with resources and materials, what should we build and how should we build it? One of the things to keep in mind is that when we're talking about infrastructure, we're talking about making things real. So this is a quote from the Climate Change Committee in the UK, and they said, we've done a lot of talking, we've got to do a lot more doing. And that it was really the case. And if we're talking about doing a lot more doing, we have to take into account how long it takes to do things, right? So if we say, well, we can solve all of our problems, but it's only going to be with construction projects that take 100 years or take 15 years, then we haven't solved any of our problems until at least 15 years from now, which is important. It's also important to keep in mind that construction projects take a long time. This is a figure from some research that we did a few years ago. Oh, and you can't see on the scale, but the bars are measured in 25 years. So sometimes you're looking at projects that stretched over 60 years, more than that. And just for scale in my personal life, is everybody here from Ontario? No. Okay. So if you were not from Ontario, you might not have heard the Eglinton Crosstown. One of my first jobs back in 2012 was to work on that construction site. I was outside in the winter, hence the very, very big coat. And this is from a couple months ago. No one is surprised that Eglinton Crosstown is delayed again. Infrastructure projects take a very long time, and that limits the scale of what we can do. Other quote I think it's important to remember is that to accomplish great things, we must dream as well as act. So it's not enough to just do things. We also have to imagine them first. And a lot of our imaginations about the built world are, I think, pretty silly. I enjoy these equally the same pictures of the autonomous car, autonomous future from about 100 years apart. It's important to keep in mind what actually is innovative, what actually is different, and what would actually change things. And just because you've heard an idea a lot of times, the idea that it's innovative, the idea that would make things better doesn't mean that's true. And I know we're talking about buildings, but of course, buildings and transportation are very heavily connected to each other, and building design and land use planning completely governs whether or not we need transportation. And our most ambitious planning is taking something right out of 1918. It takes a long time to invent new things. This is a figure from how long it takes from things to go from, it's a good idea in the lab basically we're using it at minimum scale. So we sort of have a 4 to 5% penetration. And basically everything takes at least 50 years. There's a couple things that have been faster, like a nuclear power, jet aircraft came out pretty fast. But even nuclear power, it wasn't real until 1950 and didn't start happening in a real, the chemistry, the math didn't exist until 1950s. It wasn't real on the ground as infrastructure until the 1970s. At that time around, if we started now, nothing we would do would be ready for 2050. So if we're talking about climate change, it's too late for new ideas. We have to just use old ideas. So what would I say are the ingredients for near-term success? And I promise I'm going to get to buildings. Like 1, stop making the problem worse. 2, rely on technologies that are ready for diffusion. So rely on things that are already usable. Be ambitious with rollouts, pursue beneficial lock-in, and prioritize shared spaces and infrastructure. And there I really don't mean Uber, and I will get to some examples. And when I say things that rely on technologies that are ready for diffusion, I remember, in the solar decathlon of houses when I was in school, everyone was using phase change insulation materials that would suck up a whole bunch of energy as the temperature. Like, that's cool, but it's really expensive and it's not ready. It's not market ready even now. There's a ton of things we can do, like just regular insulation and electronic heating that is ready for diffusion. So go with regular insulation, not phase change insulation. It's much more likely to help. So some examples: technologies ready for diffusion, things where there's already some local niche. So if it's being used by some people, so some people have experience with it in your community, it's going to work a lot better. It's much harder to start something from scratch. So, you have tradespeople who know how to work with masonry. Great. See what you can do that's better with that skill set. It's going to be a lot easier than importing an entire new skill set. If you don't have anything useful locally, import a niche from somewhere else, somewhere where people can help you. If the closer it is, the better. And the lower technological complexity is the things that you're ready to use, the easier they're going to be. So for instance, things within the built environment that are ready for diffusion are missing middle buildings and bike lanes. Go big and fast. You want to do things at scale. A little bit of a project that doesn't make much of a difference, and you have a very short window to act. So if you do things that work, you build political momentum, you align with political cycles, so you're less likely to get completely washed out as policy changes, and that you build an example other people can copy. When I talk about beneficial lock-in, I mean, do things it's hard for people to undo. So a lot of European cities have better buildings that are much more sustainable than we are because their block scale, their blocks were set up before the invention of cars. And that's really, really hard to undo. And so they still have blocks like that where it's hard to take cars. They have higher density. In Seville, Spain, very famously, when they put in their bike lanes, they just did them. They did them really fast and at scale. And they did them at sidewalk level rather than street level, so that if you wanted to take them out, you'd have to jackhammer out all the concrete. They were very popular and people didn't want to take them out, but it would be really hard to take out Seville, Spain's bike lanes. The London Underground is another example of beneficial lock-in. We have this also in Toronto. The legacy of that infrastructure continues to make the city more sustainable, to make buildings work better there. And that you can be purposeful about this. So 2 of the examples are old, but Seville's is new. You can be purposeful about doing things that are hard to undo. Another thing is shared space. So I've written about this in a couple different forums, but if we want sustainable buildings, they're going to have to be smaller than the current norm of buildings. The average Canadian lives in about 60 square meters of space. What's globally sustainable is closer to 10 to 15 square meters. Now, do I think we're going to get down to that number? No, but we can't keep building 60 square meters. We also can't afford it. If people are going to have less private space, they need to have much better public space than we build in North America. And just some pictures I've taken, basically none of these in North America are what really good public space can look like. The really snowy one is in Toronto, but is in Ontario, but completely unreachable without a car. Okay, so some framing of the problem. Now I'll talk specifically about buildings. So can we take this problem of time and resource limits and needing enough housing and apply it to how to make better buildings? And specifically for this framing, I'm working on the donut economics framings, the safe operating space for humanity. The general framing is this: is we have an ecological limit. We can only push our ecosystem so far before it snaps back at us. So there's only so far we can push it. We've already pushed it quite far. That limits how much we can consume. There's also the social foundation, the inside. People have to eat and breathe and live somewhere, and we want to have as many people as possible reasonably accommodated within their needs in our community, in our country, and the planet. And so that pushes on our consumption space. And in between those two is the safe operating space for humanity. So in our research, we look at what the greenhouse gas budget is, what the minimum infrastructure and housing we need to meet our needs, and then the tasty part of the donut: material efficiency, urban form, building form, structural design, material design pathways to fit in between the two. So that all sounds very doable, but now let's put some numbers on it. So we started doing research and saying, well, what could our future GHG budget be? And the first problem we found was that in construction, we didn't actually know how many GHGs we were emitting. We knew it a little bit per building or per meter squared, but we didn't know it for all the buildings all at once. And it's not included in any climate change reporting. The way that construction is handled, it gets divided up in a lot of different sectors. So we were able to use a method called environmentally extended economic input output and calculate for 2018, which was the latest data that was available, how much GHG emissions there were from construction in all of Canada. And we found that it was about 90 megatons, with about 60 coming from in Canada and about 30 being imported from outside Canada. So when we buy steel from China or the US, it's our consumption that is making the emissions associated with that steel, but it's actually happening in China or the US. And we're only promising in our Paris Agreement to reduce emissions within our own territory. Those become China and US's problem. Though, of course, it is our consumption, and it happens the other way as well. If we sell steel to the US, it's still our problem, even though it's consumed in the US. So we have two commitments at once. One, we want to reduce by 40% by 2030. So that 60 goes down 40%, and you get this smaller second bar. And we also want to more than triple construction to meet our housing needs, and that gets us this great big bar. If you look at the difference in between the second bar and the third bar, the difference is 83%. So how did all of a sudden we go from needing to reduce emissions by 40% to 2030 to needing to reduce them 83%? And the thing that we never talk about when we talk about buildings is that if you want to make more of them, each individual building has to get more better, right? So if you have 10 rubber balls and you want to use half as much rubber, you make 10 rubber balls with half as much rubber. If you have usually make 10 rubber balls with half as much, and you want half as much rubber, but now you're going to make 20 rubber balls, half is no longer good enough. Now you need a quarter as much rubber. So our background systems of how our materials are manufactured, the steel industry is getting a little bit better, the concrete industry is getting a little bit better. Even if we're ambitious about what they can do in the next decade, it's still 80% because 83 and 78 round to the same number. So we're still at 80%. So each individual building we design has to get 80% better. So keep that in mind. So then we started saying, well, is there a way we can do that? Can we build as much 5.8 million homes in Canada and get our construction emissions, our embodied GHG emissions 80% lower? So we started modeling every neighborhood in the city, in the country. And so at a neighborhood scale, we modeled as if we were building them with modern technology, every single building, every single road, and every single water pipe. And we quantified for every neighborhood in the country, if we were going to build it new now, how much housing it would provide and how much embodied GHG it would take to provide that neighborhood and that housing. And what you find is that the lion's share of the embodied GHG is in the housing, with about an order of magnitude less per neighborhood in the roads, as long as there aren't a ton of roads, which is why you see the double hump. Sometimes that second hump is because we have as much roads as we have housing, but that's not usually the case. And then water infrastructure is another order of magnitude down. Two things that we found are very important. If you look at the graphs on the right, you see that as the percentage of single family dwellings in a neighborhood goes up, its embodied GHG per capita goes up. So there's a wide spread because there's lots of different neighborhoods, but you can see that trend as you go from no single family homes on the left to 100% single family homes on the right, it just gets more GHG. We also found the opposite, that as your population density goes up, your embodied GHG goes down. So let me show you what that looks like. So in Toronto, in a sort of typical suburban neighborhood that looks like the picture shown, it takes about 26,000 kilograms per person to provide the housing and infrastructure to live there. And that's not even just to operate it, that's just the embodied GHG. In a neighborhood that's a little bit denser, more townhouses or stacked townhouses, you see half, 13,000 kilograms per person. In the high-rise neighborhood like this one with a lot of parks, again, you see pretty similar numbers at 16,000 kilograms per person. And in a denser neighborhood that this one still has quite a bit of parking lots, there's a lot of room for housing there, you see 10,000 kilograms per person. And this is sort of the range we tended to see. We can do that again for Edmonton. Same thing, single family neighborhoods, always in that sort of 27,000 kilogram per person. You go any denser than that and you get approximately half to a little bit less. It doesn't really matter if it's tall or missing middle, just goes down. If we look across the country, the single worst neighborhood in the country is on the East Coast. Now you might be looking at this and being like, well, that's a farm, but it's not. It's just people living with single family homes on plots of lands the size of farms. So there's a lot of infrastructure, very little housing. And that's a place where you would have as much materials in the roads as in the buildings. You see a lot of this sort of classic mid-20th century subdivision, which tends to be around 26, 27, 28,000 kilograms of CO2 per person. And then the best neighborhood in the country is the Plateau in Montreal, which is very high density with basically stacked apartments, missing middle. You know, there'll be long railroad style apartments, one on top of the other, often 3 or 4 per building, attached to other buildings with 3 or 4. That neighborhood has been through many different things. It was originally an immigrant neighborhood. It's been a student neighborhood, but there's also lots of families there. And this is sort of the scale you see across the country. Then we tested what are 5 different strategies to make better buildings and better neighborhoods, and what are their impacts. So you could change the form of the neighborhood being built. You could design the individual buildings better. You can improve the background systems like the material manufacturing. You can repurpose existing buildings for more function, and you can do infill. So you can build where the infrastructure already exists, so you don't have to build new infrastructure. If you're changing the form of neighborhoods being built, we found there basically wasn't any difference what type of more intensive use you did. As long as you went from single family to something else, it got better. So it could be taller buildings, it could be shorter buildings, it could be missing middle, it could be not, it could be mid-rise. Overall, they tended to work out very close to each other as long as it wasn't a single family neighborhood. Then within our data set, we have hundreds of buildings. Some of them are better designed than others. And so if we say all of our future buildings will be designed at least as well as our top 25% of buildings now, then that makes a big difference. So what does better mean? So no or small basements, lightweight materials, so don't waste materials in the structure design, no transfer slabs, efficient use of the floor plate, so we're not wasting a lot of potential housing as hallways. And often that meant smaller, particularly single family homes. If they're smaller, are much better single family homes. Smaller doesn't have to mean crappier. It can also just mean better designed, because right now we design a lot of wasted space into our buildings. We replace good design with inefficiency. So we make up for designing our buildings badly by just putting lots of extra space into them. We have some work we've done recently where we look at, there's this general, belief that taller buildings have more resource and worse for the environment, have more embodied GHG in them. So we tested that from 5 to 20 stories. And we also tested if you make your slabs thinner and thicker. So an average concrete slab would be between sort of 200 and 250 millimeters thick in Canada. And we tested what kind of difference that will make. And once if you go to a thinner slab, how much embodied GHG will that save you? All of these totally kosher within code. And even taking simplistic designs, we haven't done any fancy code. We've taken very simplistic, easy approaches to deflection. And what we found is the slab thickness is way more important than the height. That you can have an extra, 15 stories of building if you make your slabs thinner. We've been testing this in the lab, and actually it looks like we can even go to 120 millimeter thick slabs, which is even thinner than what we tested from a code deflection standpoint. It makes it a little harder to build, but it also makes it potentially quite a bit cheaper because you save a lot of concrete. So have extra stories, have thinner slabs. Aligning your columns so that you don't need transfer slabs also makes a big difference on allowing you to have thinner slabs. You can also improve material manufacturing. This will be slow. The Cement Association has an agreement with the government on reducing their GHG emissions. The Cement Association is talking about one. There's already pathways to source better insulation, but there's only so much we can do. And it takes time. We can repurpose existing buildings for more functions. So take a building and put more units in it. That requires a lot less materials than if you're building a new building, generally about a third the amount of materials to add housing. Of course, they're each individually smaller than where you started, but often, again, we had all of that wasted space. And then another thing is infill, right? You can tear down buildings and build something bigger, or even extend buildings, and then you don't have to build new sidewalks, new roads, new transportation, new sewers in the same kind of way. If we're talking about time, some of these can be done now from a technical perspective. From a political perspective, there's a different temporal measure, but I'm talking technically. So we can change the form of the buildings we build now. That's technology, knowledge, construction techniques we've had for centuries. We can go back to building better neighborhoods immediately if we wanted to. We can design better buildings now, right? All we said was go the top 25% of buildings we already built. We weren't even going past what we're currently doing. Well within our code, we don't have to change any rules. We can design better buildings now. Material manufacturing is improving, but slowly, and it's not going to happen at the scale we need to save us until probably at least the 2040s, and that's optimistic because it relies on a lot of carbon capture and storage, which is not scaling up. Steel manufacturing, for instance, has gotten much, much, much more efficient over the last 100 years, like 4 times more efficient than it used to be, but we use 38 times more steel. And so we are swamping our improvements with greater consumption. And if anybody tells you we can just recycle materials to solve that, don't believe them. There is not enough there's not enough waste material anywhere to solve that because there are more people on the planet consuming more materials. In Toronto, the total mass of all of the construction materials we tear down in a year is 4% the mass of new materials we consume. So even if we perfectly recycle that, which we can't because a lot of that is concrete, which is near impossible to recycle without downcycling, it wouldn't be that useful. You can repurpose existing buildings. We can do that now to a limited extent. It would be very hard to scale that up to solve our housing problems. And we can build where infrastructure already exists. So we can do that now. But it's really worth keeping in mind when you think about solutions, what can you do that's temporally relevant? So if we look at the entire country of Canada and the 5.8 million homes it needs to build by 2030, if we go with just building as usual, the dark blue is where our embodied GHG would be. And this is just for housing and basic infrastructure. There's a lot more that would be above this. So take the numbers as relative rather than total. If we go to a high growth scenario where we build enough housing using business as usual approaches, that's the addition of that purple bar. So we want to get this waterfall graph down below the federal 2030 target. So if we change urban form, if we stop building single family homes and build basically anything else, we can make about a third of the gap. If we improve materials, it makes about 10% of the gap, even though the materials themselves improve over 25% over time, because they're not 25, it's not an immediate improvement, it has to ramp up. So it's not 25% in year 1 or year 2, it takes time to get to that 25%. So it turns out to only be 10% over this decade. If we design better, and again, just as good as our current 25% best buildings, not even better than that, that makes up about another third of the gap. We use existing infrastructure a lot more efficiently, so we do a lot more infill and a lot less sprawl. and we do better repurposing of existing buildings for greater function, we can get these below the line. And you can turn these levers up and down to do more of one than another, but just to show it is possible with existing technology, without magic, with the skill sets we already have, to consume enough less materials while still delivering housing people would recognize and many people across Canada already live in. This is all within the norm of things that already exist in Canada. Our sample size was only existing Canadian neighborhoods. It's possible. So I would start to wrap up by saying that we have to act as well as dream, right? Most of the action on climate change has been making plans. We've done other research where we talk to people about their climate change plans for meeting their targets for 2030. And they were basically like, our plans are to have meetings and make plans. It's too late to have meetings and make plans. Stuff has to actually happen. And people involved in buildings and infrastructure, engineers, architects, planners, policymakers, are holding the levers in our hands of real things that are turning into real emissions, real pollution, real physical reality all the time. We can't be like, oh, we're going to make plans to do something 10 years from now. I think this has been maybe a mix of optimistic and depressing. So I'm going to leave you with a message because I want to end more on optimism than depressing. A separate stream of my work, I study the emergence of change. And a great way to look at the emergence of change is sewage infrastructure in the 1900s. So you've probably heard bits of this story. Cholera came to London and people were just dying in waves, mass pandemic every few years. Imagining what we went through in 2020, but over and over again, and people would be healthy and then dead the next day. It was just really, really terrible. In mid-century, a famous doctor named John Snow, not the TV character, the doctor, figured out that contaminated water was a big part of the problem. And basically, London was drinking their own poo and it was full of diseases, and that was a bad idea. So then Joseph Bazalgette was engaged to build the sewer system of London, which they still use today, which ended cholera in London. How long do you think that took from, massive pandemic where people are healthy one day and dead the next? Water is a problem, doing something about sewage. Any guesses? You can unmute yourself or just yell or hold up hands. I can't see. Usually people, depending on how they've heard the story, some would say 5 years, some it's 10 years. It was more than 40 years. And the lifespan of people in London at the time was about this. So most people who were alive when the cholera first arrived were dead before sewers happened. And they fought about taxes and they fought about technology and they were wrong on the science, and people didn't believe about germs because you couldn't see them. And it was just bad smells that made, every possible thing. The politicians didn't act until it seemed like the government itself might have to move because it smelled so terrible from all of the filth in the river. In Toronto, where I live, there were 3 referendums about building sewers while people were dying of disease that were all turned down because people didn't want to pay taxes. At the same time, so much shit piled up in the harbor that the boats couldn't dock. But this is my toilet. So we are not the first to wrestle with problems. We are not the first to feel stuck with our problems. We are not the first to wrestle with people believing in the science or the math. It has always been like this. It's not that they built big things and we can't. They built big things in exactly the same hard ways we are trying to change things, and they just kept going until we all had flush toilets. I would say when you're tackling big problems, think about what can be done to deliver tangible, real benefits in the short term. What can be done within the political cycle and what is long-term? We need to do all of the above. And when it comes to climate change and better buildings, a lot more of the first 2. And thank you for having me. Happy to take any questions. And thank you to the 2 people who kept their cameras on for all the smiling and nodding. It makes it much more pleasant to present. So Danielle and Bettina, I really appreciate it.
That was incredible, Shoshanna. All stuff I've heard, other than some of the very specific research that you've done. From a
just an indoor quality perspective, I'm curious about the thinner slabs and how that might affect things like sound transmission.
Yeah, it's a reasonable question. I don't know the answer. Thinner slabs are completely standard in many places. So, for instance, in Argentina, where one of my students is from, 120 to 150 millimeter slabs is completely standard. Sound transmission does best with voids, right? It's a thicker material. It's still going to transport sound, and so I think it's a solvable problem again with design. Where if you made a void, I think that's better than solid. Also, if you need to have material, does it need to be concrete or structural concrete? Like you could even just pour some sound resistant concrete if that becomes a thing. It's a problem that other people need to work out, but we're pouring 35 MPa concrete that we do not need. I didn't say this, but I don't know how many structural engineers there are. All of our really super thin slabs were with 20 MPa concrete, so way weaker concrete than we usually use. That's what you make sidewalks out of. So our slabs are too thick and they're too strong, and we don't need it to be any of those things. Am I supposed to wait for hands, or were there questions in the chat?
I can go next. All right, so my question is a bit more open-ended. Do you think it's a case where we need to be a bit more stringent in like policy making, or it needs to be a bit more individual efforts focused, or a striking balance of both? Because it seems like the solution is everything, but also nothing, and I don't know.
There's definitely no one solution, and waiting for one solution is a recipe for nothing to work, because then you just wait for it to magically appear and don't do anything.
Yeah.
I have a colleague, remember telling me, he looked like a great success, and he's like, I'm an overnight success after 40 years of work. And climate change is going to be like that. So I don't know if you've paid attention to what's happening with solar energy over the past year and a half. If you haven't and you want good news, you should go check it out. But there's as much solar energy being built now every month than there had been built in entire countries through all history up until like a year ago. And so what's happening in solar is just totally revolutionizing. Like everything you know about energy and climate change, if you're even like 3 years out of date, is probably wrong, because if solar is all of a sudden an overnight success after 50 years worth of work. And I think it's going to be the same. So yes, we need stricter regulation, but we need much better designers, much better urban planners. We need engineers and architects who can talk about why we should build older buildings. So for example, the Better Buildings Bootcamp is specifically interested, among other things, in climate change. So I talked today about climate change. With many people, I would have just talked about cost. Right? We need to build buildings. Materials are expensive. We're designing in a way that's wasting materials. And so I say, I'm talking to owners, I'm like, why don't you pay your engineers more so you can save millions of dollars in construction? And they go, what? Right? So there's a lot of different conversations we have to be having. It is not just your responsibility as an individual, but you are also not excused from not carrying the burden. So we have to do both. I can't solve it alone. You can't solve it alone, but we all have a responsibility to be engaged. And so it's going to be all of those things. We need better policy, but we also need better design. We need better communication with clients. We need better clients. We need the insurance industry to pay more attention. And then maybe one day we'll be an overnight success. Hopefully it's 5 years from now or 2 years from now, but it might be 10.
With your years of experience, do you think there's less or more resistance now?
Oh, so much less.
Okay.
When I started to study embodied carbon, I was told I was engaging in academic masturbation.
Yeah.
Oh, I said masturbation and someone put their hand down.
They're like too much.
I have a question.
Yeah, please.
Okay. So you can all hear me, right?
Yeah.
Okay. So I wrote it in the chat. So thank you so much for this presentation, by the way. It was super informative. my question is related to the growing pains of the process of developing infrastructure. I just use the word growing pains because I can't think of a better term. But I'm wondering, how long do you think it'll take for Canada to kind of develop through it? Because obviously, as you mentioned in London, there were times where people were like, my taxes, and they were developing the system for the sewage and the pipes, like the system to make sure that the disease wasn't spreading as much. And there would have been people pushing back against that at that time because they were probably thinking, oh, well, it's the way it's always been. We don't want to pay tax dollars towards this, all of that. And I've been thinking a lot about that over the past year because we enjoy the world that we have now because of the people who wanted to make a change. And those were the people who were willing to sacrifice a lot at their time so that the people of the future, even though they wouldn't reap the benefits. And I'm thinking we're in that moment now. We're in a very like climatic moment, I think. So even that example of the LRT, like transition systems, I live in Toronto sometimes, like before schooling, I mean. And the LRT or the TTC and stuff is always under development, but I think sometimes it needs to be under development because it is for the future. I'm not too sure about all the details of that. But my question is, do you think Canadians' attitude towards the development will change, like the process of growing pains when we're in the in-between transitionary period? I hope that makes sense because it's inconvenient now.
It does make
but-
sense. But no, I think people will always be people. People will always complain about change. People will always be annoyed about inconvenience. People will always be annoyed about money that goes into a collective pool. I think that will always be true. I think that it has elements of getting stronger and weaker. Right? It's easier to feel like you're investing in the future when you're very secure in the present. And right now, people aren't feeling very secure in the present. And so then there's like, well, why should I invest in the future? I need to deal with now. And that's a very well documented phenomenon. So I think it will ebb and flow, but I don't think there's ever going to be any magic period where it's easy to make change, which I actually find, I'm getting asked how well I liked my own session. I'm going to say it was great. Okay. I think I find that very optimistic to remember that all of the hard things that have been done were not done in a magic period of ease. They were all hard and people did them anyway, and we're people just like them, and we can do it too. I would also remember that time passes, right? 5 years goes by in 5 years, no matter what. And I remember, I don't know, maybe I seem super old to you now, but I don't think of myself as super old. And I remember being 20 and things were impossible, right? Electric cars were never going to happen. Solar panels were never going to happen. Bike lanes would never be built in Toronto. Multiplexes would never be legal. Everyone would always have parking minimums, right? These were orthodoxies that would never change. Every single one of those things would change. I remember when we were never going to stop smoking in bars, right? These were all never, ever, ever going to change. And they changed. I have a good friend who worked really hard on the advocacy to allow multiplex construction. So to allow for any things other than single family homes to be built. And he wrote books and he advocated, and he was there 10 years before everybody else was there. And when we first became friends, we went for a walk and he was like, oh, it's never going to happen. And I was like, wait, no, it's definitely happening. I don't understand. It's like, what do you mean by never? It's obviously going to happen. And it turned out that his timeline of never and my timeline of definitely were the same. He was talking about 5 years and so was I. And I think that that's important to keep in mind. I work on infrastructure, so I'm used to talking about these timelines all the time. And it's why I made such a big deal, even though, to be fair, I was not invited to talk about time to you today. I just put it in there anyway. When we talk about problems in time, it's really important to be like, okay, we have a big problem. What can we do about it this year? What can we do about it in 5 years? And what's going to take longer than that? And to do all three of those, because the first two give people hope for the long run.
Yeah, I was just thinking that's such a great point because a lot of it is like motivation, like not motivation, but it's kind of like a lot of people don't want to do the long one because it feels like it'll take forever, but time is going to pass anyway. So it's good to have the collective hope of
There's the
we'll
classic
get
thing
there.
of the best time to plant a tree is 5 years ago. The second best time is now. I promise, we will age or be dead. And so it's fine either way, right? But like, it'll be 10 years will go by and you'll be like, wow, that happened. Melanie, you've had your hand up for a while.
Thank you.
Thank you.
Yeah, I just I'm doing my master's in reducing embodied carbon in the residential construction industry on PI though. So I'm not dealing with multi-rise buildings, and I'm about to do engage with builders on the topic. And I'm wondering, what have you experienced when talking to builders? What resonates with them when we talk about embodied carbon? Because I can't even use, like, I'm going to be doing semi-structured interviews.
Money.
Using that term or energy efficiency, like we're not even in PI, like we're just building to code. Like there's not, energy efficiency is just making it into the lingo, I think. So all of this other stuff is way beyond.
So I was actually just in PEI a couple of weeks ago for a few days. So I have an image of the urban forum in my mind. So the things we were talking about single family homes, and we've written 3 papers just on single family homes and embodied carbon. If you're interested in them and resource use, go check out my Google Scholar or email me. They're big things. One, basement's bad. And so if you want to stop people from building basements, you can talk to them about cost, right? They're very expensive, they're sort of dank, and they're liable to flood. So if PEI has any flooding issues at all, then I would take a flooding and costing, and everybody has flooding issues at this point, right? It's harder to get insured. You can't insure your basement in most of Canada anymore. So there's a good reason not to want one. So I would talk to them about flooding and about the cost and time of basements. PEI does have lots of multi-family housing of the scale that you would see people building in like the 40s and 50s, you know, where it's like 3 units in a home. And if PEI has anything around a housing crisis, I would talk about how much cheaper it is to build that kind of housing, how it fits in so nicely with neighborhoods. And I would be using pictures of similarly like rural or car-oriented or small towns that are doing it. So cost, quality of life. And then the other thing is, don't you want to know your neighbors? So if you're building big single family homes with a 2-car garage, you're really far apart from your neighbors and it's really hard to be into community. I would probably also talk about the safety of children on streets like that. So depending on a little bit on like what we're doing, those would be the things that I would be talking about. But if we're just talking to builders, material quantities, which is cost, construction time, which is cost, and basements, which is cost, and flooding.
Okay, thank you. I'll definitely be emailing you and checking out your papers. Thank you.
You're welcome.
Any experience in persuading affordable housing providers, which is the project that we'll be working on?
Yeah. I mean, generally affordable housing providers are more future oriented because they're going to continue to own their asset for a long time. So then again, cost, quality of housing, cost, flooding, cost, and long-term maintenance, flooding, and cost. Those are all the things that I would talk about. It depends a little bit on sort of what scale, but for instance, Toronto Community Housing is very interested in embodied carbon and resource costs. You know, 50% of the cost of building a building, maybe more now as material prices go up, is materials and land. So if you use the land inefficiently, that's a lot of cost. And if you use the material inefficiently, that's a lot of cost. And most people are in the building industry are very motivated by money. And it's getting tough, right? It's getting harder. Oh, the other thing you can talk about is debt servicing. When you're building underground, you're slow. So it makes your debt servicing longer. So if you limit your underground construction, then your construction is faster, you have less debt servicing, which again is cost. And if you align your columns, it's easier from a constructability standpoint, which again is cost. The nice thing about embodied carbon is if you're doing it well, it saves you money on embodied carbon. If your embodied carbon approaches are making things more expensive, you're doing it wrong. Yes. Disagree with me, but hard yes.
Natural building materials, I'm going to argue with you. Currently, for whatever stupid reason, are more expensive.
But natural building materials aren't better for embodied carbon. They can appear better if you're created with your math, and they're lighter, which can make them better for embodied carbon, but they're not naturally just better. Often people still put a 4-layer garage underneath. The overlap on a wood building and a concrete building in embodied carbon is really high. You could just design your concrete building better. Also, again, this is a time thing. Our capacity to ramp up, especially tall natural material buildings, is really slow. And by the time we ramp up that industry, the concrete and steel industry should have improved enough that it's very unclear it would be better. It does not make sense to me to try to build a 30-story building out of wood. Similarly, one should not build a 4-story building out of concrete. Farouk had his hand up.
Yes, hi. Very quick question. The one thing that I've seen interesting with the house, I know that housing market is very expensive and is very challenging. Also know that because I was in the project, I designed and built 3 houses here in the GTA. But the one thing that I have known is that there are new houses that are being manufactured design that is like a box. So they manufacture these houses, and you don't need to start from excavating, creating the foundation, and then build a structure. They just manufacture that box and they place it, and the box becomes opened, and then it turns into a house building or a house room. I don't know if you have seen it, but if like, let's say, are we being dragged into that era now that we are?
You can't provide enough housing on that type of light structure. So I've seen the things you're talking about where you unfold like a shipping container, and they can provide rapid sort of apartment sized homes. And I agree with you, they're really interesting, make for really cool videos, but they're not a big scale answer to it because they're too spread out, right? So for cities, you can't have your housing continue to spread out like that. You can't house enough people. There is something similar, which is prefab housing, which there's more and more of, and the federal government is pushing. That all does require foundations, right? Anything heavy requires a foundation. I suspect even those foldable containers need a foundation underneath because otherwise they'll sink over time. So you don't have to build a basement foundation when you build a prefab building, but you have to build a foundation of some kind. So you have to pour, oh, he disappeared. Oh, there he is. To pour a slab, at least for your building. Prefab buildings can be better for resource use and embodied carbon if the designers take the time to make them. So there's been a lot of research on, is factory made housing better for resource use? And the answer is, yeah, it can be. It's an opportunity. It's not a guarantee. So if you design well, you have the advantage of all kinds of quality control. You have the advantage of you can do reproducibility. You have the advantage of you're incentivized to be efficient with your space and materials, but it doesn't happen on its own. You have to want it to happen. There's also another thing that happens, which is a lot of factory made housing is wood. And so you end up with a lighter structure and also a lower height. So again, like wood is great 4 or 5, even 6 stories, and will beat out concrete at that height because it's just a lighter structure. But you're not going to have a prefab building in the same way that's like 20, 25 stories, at which point concrete starts to win pretty dramatically. Did that answer your question?
Yes, it answered my question.
There was a question in the chat. What are your thoughts on using temporary housing solutions built on unzoned or barred plots of land and designed to be dismantled and re-erected somewhere as a response to the current housing crisis? I saw it somewhere and wanted to ask. I think that there's lots of reasons to have rapid intervention housing. I don't see any reason why we should build on barred land. Like, we shouldn't be building on forests. Also, assuming you want to go to the toilet, you can't. So if you unzoned land won't have any services, so it won't have water or sewage or electricity. And so it's not very practical. In Ontario, when the provincial government wanted to force development in the Greenbelt, this was a major practical obstacle, amongst it being a bad idea for many reasons, was that there was no services. There are lots and lots of places currently serviced where we could increase density or even have rapid delivery. So I don't see any reason to do it on unzoned. I'm not sure what you mean by BARD, but I'm going to assume protected land. I see absolutely no reason to do that. The other thing is that temporary constructions are almost never temporary. There's a great story from York University after World War II, when soldiers were coming home and there was a big push to send people to university. They built a temporary building. In the 1990s, they took the word temporary off of it. David.
Yeah, I guess I had a question. So with the popularity of addressing embodied carbon, I know when you do like LCA or life cycle analysis, you have to consider transportation and manufacturing for materials. So do you think that we're gonna see more materials for construction being manufactured here in Canada in a response to reduced transportation and manufacturing carbon?
So within the embodied carbon upfront, so there's A1 to A3, which is the extraction and manufacturing of the materials to get it into something what you would recognize as construction materials. Then there's A4, which is transportation from the factory to the construction site itself, and A5, which is energy use on the construction site. Of that, let's say it's 100%, about 80-85% of it, up to 90%, is the extraction of the materials and the processing of the materials into what we would recognize as construction materials. Transportation is sort of 7 to 8%. On-site construction is another 7 to 8%. So if we're talking about the low-hanging fruit, transportation is not that relevant. And if you're shipping things, the boat itself is actually very low GHG emissions. It's the truck on either end, which is most of the GHG emissions. And that happens also with local things. So I don't see greenhouse gas emissions from transportation being a driver of change, because it's just kind of in the wash of all of the other things that we do. The European Union is getting pretty intense relative to the rest of the world on import of materials and sort of border taxes on emissions. Canada hasn't said they want to do anything like that. Also, we currently manufacture already about 2/3 of our overall emissions. So we import only 1/3 of our materials. We're a very big country. We make a lot of our construction materials. Most of our steel is from here. Most of our concrete is from here, with our big import partners being the US and China. And I could imagine political or financial reasons that changing, or some of the balance, like we import steel and we export steel, maybe we'll see less of that with the tariffs. But I don't expect GHG emissions to be a driver of that change compared to the other big political pushes we're seeing at the moment. And unlike the European Union, I don't think we're heading into a short-term period where environment is going to be a top governing press. Does that answer the question?
It does. Thank you.
Farouk.
Yes, so I'm wondering what's the solution to create more housing in the GTA, and what action can be taken so that the housing market will become stable. I'm asking this question because I believe there should be a change in order for more houses to be created, and there should be a method and a technique for the housing market to be stable. Because
do you mean houses or homes?
Houses.
Okay. There is no sustainable solution to deliver more houses. So the only way to get more houses in the GTA is to sprawl. And that would make things very bad for the environment and also very expensive. You can make that cheap if you do what's called sweat the infrastructure or do a bit of frankly, a Ponzi scheme. So the way houses used to be made cheap in the past is that they wouldn't fund any of their infrastructure. And so you would get, I'm being simplistic because we have limited time, but you'd get a new neighborhood, you would develop it. It would not have enough taxation or money to support its infrastructure, but that would be fine until things started to age. And then it would really not be fine because everything would break and the density is too low to pay for anything unless you have super, super high taxes. And then you have to sell another plot of land. And so that's the type of development that happened a lot in the GTA, which is how we got so big. And lots of communities funded their expansion by selling more land and then ran out of land. Someone's asking, what's the difference between houses and homes? So a house is like a standalone house with, you can imagine the house character. A home is a place where people live. Homes take many forms, including apartments, townhouses, condos. There's many, many ways to deliver homes. They're not houses. So there's no sustainable way to deliver more houses. It's a physics limit. We have people and there's a limit on people and space. We've run out of space for houses unless we tear down some of the big houses and build more smaller ones. We can get more standalone houses by doing backyard or laneway housing, where you have big plots of land and you just fill it in with more houses. So that can get you more standalone houses. That's been very popular in California, where they don't want density, is building a lot of houses in people's backyards. They have to be smaller and the infill on the land, and that can work okay. I think about, I can't remember if it's a third or 40% of all new housing in parts of California have been like that. If you want new homes, then there's lots of ways to do it. And there have been, over the past 5 years, massive changes in what is legal to build in the GTA, but also all around Canada. Most of Canada has, for nearly 100 years, had zoning that requires you only build one house on a big plot of land. And that is increasingly changing to say you're allowed at least 4, either arranged in some sort of horizontal arrangement or stacked on top of each other. And of course, if you multiply things by 4 times, then you have a huge amount more housing. Like 4x is a big multiplier. In terms of construction techniques, it's also very efficient in terms of people. Like one of our issues in the construction industry is we don't have enough construction workers because they're aging out. And so if you take one group of, it's not that much more work to build 4 homes on the same plot of land or one house. And so you get a lot more efficiency on your workers and also on your materials, and it makes things cheaper because there's a lot more shared walls and shared workers, shared yards, and all of shared roads and sewers. So the distinction between houses and homes is really important. We can have many more homes. We can't really have more houses.
Wonderful. Thank you. Oh, I think we could sit here for hours just asking you questions. You've been amazing. Thank you so, so much.
Thank you. Can I respond to the laneway homes?
Yes.
Thing in the chat. So we have, over the last 7 years, quantified the embodied GHG in 200 different buildings, some of them, 50 stories tall. The single worst in our data set is a laneway home. And the reason it is the worst is because a lot of laneway homes that's currently being built are basically parking garages with a single bedroom apartment on top. That is a very small amount of housing for a very lot of materials. One of the easiest ways to make housing of all types cheaper, faster to build, less polluting, is to stop having indoor parking. So big buildings, single family homes, parking often takes up 20 to 30% of the square footage or more. In things like a laneway suite, it doesn't actually house any humans. And it's very expensive. It's usually made out of concrete, and the building code requires you to treat it as outdoor space. So you have a huge amount of insulation, which is also massively GHG intensive. So laneway homes can be a great infill way. If you had the choice in between a laneway and a multiplex is much better. And laneways with parking, especially if the parking is new, are very inefficient. Thank you for having me. Sorry to...
No, are you kidding? Thank you. Thank you. Thank you. Thank you.